Can you hear me? Okay, good. First of all, where is Groningen? Groningen is the last city in the Netherlands before the North Sea. It's a typical student city. This is the oldest building, which is 1625. We are full of channels. We have a tower, like in Pisa. And the telephone prefix is 050, like in Pisa. There are 40,000 students. Total population is 170,000. And we have in Dutch an old saying, er gaat niks boven Groningen, which means really, literally, there is nothing above Groningen, but figuratively speaking means there is nothing better than Groningen. Good. My job is actually, I'm a professor in chemical product engineering. I started there in 2003, where there was one professor, one assistant professor was me at the time. We had 2 PhDs, we had no equipment, nothing. We had to build up from zero. At the moment, there is 2 full professors, 2 associate professors, 3 assistant professors, and a 4th one is coming actually at the moment. We have 6 postdocs and 31 PhDs. Usually we have like between 60 and 80 students per year, master and bachelor. Most of them doing their thesis with me. As a matter of fact, I broke the record of the faculty this year. 430 students made the bachelor and master thesis with me. I'm very popular, especially among Dutch students, especially the German ones also. Of course, we are an academic group, so we have publications, but we have also 8 patents, and 3 more are on the way. Actually, one has been published actually a couple of weeks ago, and 2 are commercial products, and both are actually our ideas. I will show you today one of them. We have an extensive industrial network, business to business, but also business to client. 90% of my research is actually together with companies, so I'm from the dark side. Okay? Good. Why I'm here? Well, the reason is that when I did my PhD, this was one of my supervisors, Professor Mauro Aglieto. Unfortunately, he passed away a couple of years ago. Professor Mauro Aglieto, when I was a PhD, was secretary of IEM. And one day in 1997, he told me, well, there is somebody who would like to organize a conference for young people. I didn't know at that time that somebody was actually sitting in front of me right now. I knew him a little bit later. Well, and then I helped organize the first and the second edition from the background. I don't like the spotlight, but I like very much to help on the background, which I did. What I would like you to do is to pay attention for the next 20 minutes and go home with 3 messages, 3 takeaways. 1, networking is essential in science, also between people, and reversible is crucial. That's me, is my quotation. Second one is, iedereen nadeel heeft zijn voordeel. Probably the German guy can understand this, no? It's Dutch. Johan Cruyff said that, was a very famous Dutch football player. It means every advantage has its own disadvantage. I teach my students, every time there is a disadvantage, look around whether you can turn it around and play in your advantage. I will make an example also of this. And the third one is what Mauro Aglieto said to me in 1997, bisogna pensare in maniera differente. We have to think in a different way, and especially young people, you have to dare think differently. Do not conform yourself to old people like me. Dare to think differently. In Dutch, we have a wonderful verb for that. It's called omdenken, thinking around, which is actually what young people should do the whole day. Good. Networking. Well, I will briefly talk about material recycling, so just for you to have an idea. What is material recycling? Most of you probably already know. This is a foil rubber which is used in the Netherlands for roof protection. So you put it on your roof, it protects from rain, and it protects actually from UV light. If you want to do material recycling, of course, that means that somehow you have to find a way to go from this piece of rubber to another piece of rubber. If you can make the same product, then you are doing cradle to cradle. If you cannot make the same product, then you can make other products, but you still are recycling the material. If you don't do that, there is chemical recycling. You can still get chemicals out of it, like this BTX, which is very famous actually for the chemical industry. And what is not allowed to do anymore, at least in Europe, is to burn it. My job, and what I do as a research, is actually on this side. I have many colleagues doing on this side, and I think also some people here in the room do this side of the story. But I do this. Good. So what do I do? Well, the first thing that I do, that started many years ago, I try to design material so that it can be recycled at the end. The problem with rubber is that they are polymers, but they are cross-linked. There is sulfur in between. Well, there was a poster from Pirelli in which they tried to actually use another cross-linking chemistry. But you have to be able to, let's say at the moment, recycle polymers which are cross-linked with sulfur or even with carbon-carbon bonds, which is a challenge. So when you recycle things, you think, well, I recycle, I make slippers, and I make very low-value products. This is not so. So just to give you an example. This is a material that we made many years ago, number one, and two is a reference rubber, and a PDM rubber, which you can find today on the market. These are pieces of rubber. So that means that if you attach them to an electrode, and you stream a little bit of electricity into it, they are still very flexible, so you can twist them. Oh, Francesco, do they pay you also all this money to tell us this? We know this. This is rubber. We can do this every day. Well, what is peculiar about this is that when you remove the electricity, you don't stream electricity anymore. The normal rubber goes back. My rubber stays in place. This is called current-induced chain memory effect. So you just stream a current, and the material stays in the form that you decided. So these are very nice materials. They are self-heating. They can repair themselves. So if you scratch the surface, you can stream electricity. You can put them in an oven. They will be repairing themselves. Our response to electricity, well, all the people, they might remember the song. I named this effect Twist Again. Twist Again, yeah? You remember, good. They are recyclable, cradle to cradle. That material, you can recycle 7 times, you get back exactly the same properties. No problem whatsoever. They might display chain memory, not all of them. Again, electricity. And all of the ingredients that we use to make that materials are commercially available. So if tomorrow you want to make it, you just have to buy them, combine them in the way that you want to combine them, and then you are done. So how do we get here? Say, Francesco, why don't you get the Nobel Prize? Well, it's very simple. It's not my idea. All of this started actually in 1996. My PhD supervisor at the University of Pisa, the second one, Professor Ciardelli, had this idea. I said, why can we connect chains, polymeric chains, with reversible bonds, like the suspension bridge in the castle? So something which we can open and close on command. Well, probably I was not a good PhD. I was not able to publish anything. We tried, but we failed. But I'm a very stubborn person, so I thought, okay, well, let's go on. When I moved to Groningen in 2005, my boss, Tom Broekhuis, who used to work for Shell, introduced me to the world of polyketones. Those were the last commercially new polymers made by Shell in the 90s. These are alternating copolymer of ethylene and propylene with carbon monoxide. And then in 2012, a friend of mine from the University of Pisa was visiting me. He's sitting here in this row. And Andrea said, well, why don't we put carbon nanotubes in it? Because then your material will be responsive to electricity. You can say a lot of bad things about me, and all of them are right. But one thing that I do, I always listen. So, yeah, we combine all of this together, and then we say, okay, let's make this material. But we need to solve one problem. We have oil-based materials, but we want to make them recyclable. How to do that? Well, the idea is indeed that you have these bonds between the chains which are reversible. This is a typical Dutch picture in which you have a bridge on the channel and you have bicycle going on the bridge. So you want to, when the bridge is open, the boat can go through, and the bikes not, of course. And when the bridge is closed, the bikes can go through and the boat cannot go through. So we need something which is able to open and close on command. There are not so many chemical reactions that are able to do that, but one of them is possible, and this is what you want. Low temperature, you want the system to be cross-linked. High temperature, you want the system to be open. So that at this stage, you can recycle as a thermoplastic, not as a rubber anymore. Is it possible? The answer is yes. Is it possible if you use a very peculiar reaction, which is called the Diels-Alder reaction? The Diels-Alder reaction, you might remember from your courses in chemistry in the first year, it's a reversible one. It's an equilibrium reaction. So what would we do? We took polyketones, we modified them with a very special reaction called the Park-Knorr reaction. It's a dream of chemical engineers. 80 degrees, no solvent, no catalyst, 4 hours, conversion 100%. What do you want more? I tell my students, if you're not able to do this reaction, look for another supervisor, because I mean, easier than that is not possible. And you get a polymeric chains with furan pending groups. And then what you do very simply is you take a bismalamide and you cross-link it. And you see here that the furan and the malamide, they made this reaction, which is called the Diels-Alder reaction. And then you cross-link and you close on command. Low temperature, the system is cross-linked, is insoluble. High temperature, the system is open, and you can process it. So this is actually, my PhD did this, actually. When it's closed, it's insoluble. When it's open, it's soluble. But this is solution. Solution is for children. Does it work in the solid state? The answer is yes. So this is a DMA in which we took the sample, we make a bar, and we process it many times, 6 times, and every time we measure the modulus as a function of temperature. And what you see here is that the same bar, cycle number 1, cycle number 2, cycle number 3, up to 6, you can recycle. Well, you look at this, and Dutch people, they look at me and say, you are an Italian man, we don't trust you. You are lying to us. Say, why? Because cycle number 1, especially at this high temperature, is a little bit higher in modulus. So you can cycle many times, but you lose a little bit of modulus. This has nothing to do with the material, this has to do with the kinetics of cooling down. Because if we take the bar, shred it into pieces, and remold it again, then you get exactly cycle number 7, the same kind of properties. Just take into account, this material is comparable in terms of properties to an epoxy resins. So it's very strong, actually. There is no thermoset for which you can make this trick. So the fact that you can make, shred it into pieces and mold a new bar, that's already something which is very nice. Yeah, so we did our publications, and then out of the blue, we were very famous. A friend of mine from the University of Creta called me, said, Francesco, you are actually on the first page of the New York Times, the scientific part of the New York Times. So I say to him, oh, is that good news or bad news? Because I remember only one thing about the New York Times. Also, these two people were on the New York Times. And for younger people, I think you have to ask the old ones what happened exactly there. But we got a lot of publicity, actually, out of this. Unwanted one. We weren't looking for this. But the use of the Diazalde to cross-link polymers was not new, but we were the first one to show, actually, that you could do cradle to cradle, that you can get the material fully recycled. After this, of course, we tried many things. So we made also rubber, and a PDM rubber, which is one here. And then we made a bio-based polyester, and Professor Gorrasi was actually in Groningen for this thesis many years ago. And we started to notice some problems with this reaction. Especially, you see, our polyketones, the reversibility was 100 degrees, you could recycle 7 times. The rubber was reversible 140, you could recycle only 2 times. This polyester, the reversibility was 160, and we could recycle only 1 time. So the higher the reversibility temperature, the more problems seems to have. So from that point on, we started publishing about the problems of this reaction. Yes, you hear me right. You can publish also something that does not work, as long as you are able to understand why it doesn't work. What's the problem? Well, one of the problems is that actually, you see actually that these materials, they lose water somehow around 120 degrees. Why is that? Because at 120 degrees, this Diazalde duct loses water, and when it does, you form this aromatic ring, and then it becomes irreversible. So you have a network which is reversible, but if your temperature goes up too much, you lose that, because your Diazalde duct, which was reversible, is not reversible anymore, which is a big problem, of course. But there are also other problems. The bismuth and amide are very sensitive to temperature. So if the temperature goes up a lot, that's something that other people saw, they start homopolymerizing. And then again, you remember my first slide, eh? If every disadvantage has an advantage, can we actually use these in our advantage? The answer is yes. I can take my system, I can cross-link it with a bismuth and amide, like this. Then I bring the temperature high on purpose. I do it on purpose. I let the bismuth and amide polymerize. I go from a difunctional crosslinker to a multifunctional crosslinker. And the theory, and it's very old theory, is Florey in the 60s, the 1960s for people, very young people. Yeah, I know. The theory of Florey says if you have a multifunctional crosslinker, your modulus goes up, which is exactly what we saw. You're able to turn a disadvantage into your advantage. And recently, we also discovered this stuff here. We just published 3 weeks ago in Polymer, which is a very funny story. Actually, when you do the Diazalde, you have the duct, but the duct can react with another furan. This is called a domino effect. It's very elegant. So we published a paper in which there's a lot of NMR, very nice NMR, beautiful. I told my students, Paul, this is fantastic, it's very elegant. It's still another problem. Because if you don't pay attention, then you get an extra cross-link system. I cannot tell you, unfortunately, that we use this for 3D printing application. You never heard that from me. But actually, we are able to turn this one to our advantage. So we can make 3D printing in which we use this reaction to relax the stress after the printing, which is very nice. All of this is very nice, but let me be honest. It's not for my children. It's not also for the younger people here in the room. This will never happen. You can go to the rubber industry. There is somebody from Pirelli here. If I tell him, can you please use Diazalde to make tires, he will start laughing at me, and also rightly so, for many problems that there are in this reaction. But this will never happen. Not even for your children. You have to convince the whole chemical industry to change all their chemistry. That's not going to happen in my lifetime. Can we do something about our materials? Can we still recycle rubbers? The answer is yes, you can. By doing what Professor Aglieto told me many years ago. You have to think differently. For many years, I used to work on devulcanization. What is devulcanization? This is a rubber. These are the sulfur bridges. You basically shred it to pieces. You put it in an extruder, and you're looking for a chemical, X, is called the devulcanization agent, which is able to selectively break the sulfur bridges, if possible, without not touching the backbone. That's what everybody is doing in this field. Everybody wants to do something innovative and wants to be rubber processable. If you have only one rubber, like a PDM for the foil, for protection of the roof, the one I showed you at the beginning, that's possible. You can tweak around with the extruder. You can make sure that the reaction is not complete. You will have some degradation, which is unavoidable. But if you don't let the reaction go to completeness, you still have some chains which are coupled. So basically, if the red one is the molecular weight distribution before cross-linking, after the devulcanization, you get the green one. You get a high molecular weight, which you left there on purpose, low molecular weight, which you don't want it, but you still cannot avoid because of the degradation. And if you do this, actually, you will get a broadening of the molecular weight, but the average stays the same. So this one works nicely. There is a company in the Netherlands, actually, they're using this. But there are a couple of problems. X, these are not molecules you want to have in your company. I'm talking about diphenyl disulfide. First of all, they are very expensive. The cheapest that we found was in the Far East. We could find actually a price for 50 euros a kilo. And we need 10%. So that means actually, yeah, only in material cost, this costs 5 euros a kilo. Well, please talk with the gentleman from Pirelli. He will tell you the rubbers are a little bit cheaper than that. So there is no way. So I woke up one day and I thought, this is going nowhere. Can we come up with something completely different? And then again, either a 4-diol, a cyanadiol, every advantage, disadvantage, or disadvantage has its own advantage. Can we use the degradation in our advantage? Something we don't want. We don't want degradation, but we get it. Can we use it in our advantage and not actually in our disadvantage? The answer is yes. So we came up with a process which looks like this. You will have to bear with me for the next couple of minutes. So here is our rubber. First of all, I think most of the people that know me, they will testify that I'm an amiable person. I'm a nice guy. Until somebody gets me angry, like my wife. But that's different. But I say, let's use the brutal approach. Step number one in our process, I put the rubber, and I'm talking about car tires, bike tires, inner tubes, outer tubes of the bikes, everything. I put this in an extruder, high temperature, high shear rate. I designed the screw, so actually the mechanical stress is very strong. It's a very brutal approach. It's contrary to my character. But brutal. No problem whatsoever. We just destroyed everything. So indeed, what we get here is very low viscosity, high solubility, so our rubber becomes soluble, but very low viscosity. Muni, at 100 degrees, it's 7 or 6, even non-measurable. And let's say that I use a catalyst to facilitate this process. I will call it C. Then, if I break the spaghetti, if I have the spaghetti and I break it in two, there is no easy way to recombine it in this way. This is dangerous, very dangerous chemicals, very expensive. But there is a very nice way, this is actually from the polyolefin world, in which you cannot do this, but you can do this. You can branch it. This is very cheap. So the second step of my process is branching it. So I take these small pieces and I make an hyperbranch polymer. It's very cheap. Suppose now that we use a component to a catalyst which we call C2. And then, and that's the first product that we are going to bring into the market, we are making 3,000 now for the town hall in Amsterdam. So if you go to Amsterdam, you rent a bike, you get one of these crates for the bike. Think of me, please. What we are going to do is we add a third component, which is also a recycled polymer, and we make a thermoplastic elastomer out of car tires, of all materials in the world. And this component is called C3. So this is now an industrial process. I did this actually with a small company which is called Disrupt. And the company we actually brought my patent on this is called MBR, Newborn Rubber. They're going to open the plant. They are building it right now in a village close to Groningen, 20 kilometers. They needed a couple of millions to open the plant, but they're doing it. So this is going to be a reality. This works, in other words. Yeah, so it's a process intensification process. It's very easy to scale up, it's cost effective, and it's very robust. Well, you look at this and say, Francesco, you're really cheating us. This is not possible. You're using 3 catalysts. I mean, this should be expensive. So for the young people in the audience, when you want to make an effect on the public, you say something and then you show this. C1 is equal to C2 is equal to C3. It's one catalyst. It's a polymer, which works as a catalyst, as a branching agent, and also as something else, as a compatibilizer. It's a polymer which is in Loris shoes. It's used to make these shoes, so it's very safe. Its cost is about 2,000 euro per ton, and we need 3% of that. So for every kilo of rubber that we're making, we just have few cents of material cost, and the rest is extrusion. I'm an extrusion man. Extrusion in the Netherlands is 20 cents a kilo. We can recycle car tires for less than €1 a kilo. Turn it around completely. The crate for the bike that we made is very nice. And actually, if you take it, since now it's a thermoplastic elastomer, you can recycle 3 times, you get back exactly the same properties. So we took the rubber, which is the paradigm of something which cannot be recycled, and we made a material which can be recycled many times. I'm finishing. These are the 2 guys which had the company, Disrupt. Tom is an Englishman, and Magda is a Dutch lady. This is an SME. It's just a 2-man company. Their background is completely wrong. Tom is an economist, and Magda actually is a geography something. But they had the vision, so they start working with us for many years. They trust me, poor guys. But at the end, actually, they have their products in their hands. And of course, Tom is a very nice guy, but he's British. So when you work with an SME, you have the problem that if something happens, that relationship can be easily disturbed. So when this happened, Tom, who is a very nice guy, sends me a bottle of whiskey every Christmas. One Christmas I didn't receive it. Say, well, why? Because this. Say, and you even made it worse a few months later with this. But that's life. If you lose your network, like it happened to me, I moved to the Netherlands in 2000. I lost my network. And then a few years later, Andrea was visiting me in Groningen, and he said, wow, Francesco, why don't you come to an IAM conference? Which I did. In that IAM conference, Chiara Gualandi from Bologna said, wow, Francesco, why don't you visit us? There is a friend of yours, Loris, and other people waiting for you. If you lose your network, make sure it's reversible, like the DSLR. But it's very, very much important. So thank you, Chiara and Andrea. This presentation is dedicated to you, to both of you, actually. Otherwise, I wouldn't be here. And of course, I'm a professor. I don't work. I pretend to work. I just sit behind my computer, try to fight bureaucracy for my PhDs, and that's it. This is the list of people who actually work on all these projects. I didn't have the time to explain everything today. You will have to invite me and give me 3 hours presentation, otherwise. Thank you very much for your attention. Questions? Questions? Yeah, you invite me. It's full package. I myself, no problem. I'm 52. I play tennis. I speak Dutch, a little bit of German, Italian, English, Spanish, and that's it. No questions? Of course. Of course.
Okay, thank you for the very nice talk. Yes, I have one curiosity. The extrusion you make for the recycling is a bit energy intensive, I guess, or not? No? Okay.
We're talking about non-magnetic chairs, which are also using the vulcanization. A little bit higher. So the vulcanization of SPF, you have to carry out as 180. My extrusion is at 190.
Okay, so you do the job most.
Design of the screws.
Okay. And no, the real question is, okay, you make a recycle of metal in making a thermoplastic elastomer, which has potentially a lot of applications. But I think there are more questions. Okay, there is one question for the specific product is release of, I mean, the tire is full of strange chemicals which transform in other chemicals, so it's a bit of a nightmare. So how do you deal with the potential of release of these chemicals from zinc to 6-PPD derivatives, which are now very popular and so on? And the second question, more on my side, can you do also an elastomer which is not softening at temperature? Because of course, if you try to use this for tires, any thermoplastic elastomer or any material which softens in temperature, the problem is that when you brake and the temperature locally goes to 170, 180, 200 degrees, you slide, so it's an issue.
Thank you for both questions. I will try to answer them very briefly. Number one, No, let's start with the second one. You were spot on. The Diazalde, the reason why it's not applied is that if you take the compression set of that rubber, which is crossing with Diazalde, the normal PDM, which is crossing with sulfur, stays actually with a nice low compression set, so high elasticity until roughly 100 degrees. Then it starts going up. Mine starts immediately from room temperature. Room temperature is comparable, but from room temperature, since Diazalde is an equilibrium reaction, it goes up. For the real stuff, the car tires, I can also recross-link them again. I didn't show here, because for the crate, the small company, Disrupt, they wanted something which was the paradigm of being recyclable. So that's why I make a thermoplastic elastomer. But I can recross-link the car tires. Before you ask, I cannot make car tires. That's the reason why I have a Volkswagen and not a Lamborghini. If I could make car tires, of course, then it would be completely different. I would not be wearing short pants here, probably. We lose some properties, of course, but when we cross-link it again, we get still rubber. There is no problem whatsoever. It still has ABR or other components, of course. So we are going now, this is the first product, but it's in Dutch it's called the paraatpaardje, it's the horse for the parade, to show that this is possible. We are making actually driving plates. Those are things which are 3 meters by 1, which I use on the Dutch roads and on the Dutch bike lanes when there are works on the road. So your car has to be able to go on them. So we lose some properties, of course, but to the best of my knowledge, this is the only technology which allows you, there are other companies that claim other technology are also possible, but this one is happening for real. We are making driving plates actually, right now. This allows you actually to have the rubber from the car tires completely recycled in a material shape. We cannot make new tires. We don't have enough properties, that's for sure. So it's a form of downcycling. Release. We only see release when we extract with BTX, with xylene at high temperature for 3 days. And then we see some of the things coming up, some very strange things like pyridine, which are very strange actually. Okay, we start with a mixture of all the tires, Pirelli, Goodyear, everything. So there is everything in there. In water, for 6 months, we don't see anything special coming out, especially when we cross-link it again. Grazie.
Thank you for your nice presentation. I would like to ask if you are thinking of use another catalyst that is also recycled, so you get the entire reaction with something that is recycled.
As I say, the catalyst is a polymer. I use only 3% of that. And it's it's not bio-based, but it's recyclable.
Ah, okay.
So that one is already there. We tried also with other catalysts. We have a long list. At the moment, we have proof that, and it's also in our patent, 3 of them, they do the job. 2 are polymers, and 1 is not a polymer. The one which is not a polymer is a molecule that you can eat. So before my students actually took the risk, I actually ate it myself. I'm still here. So although the food yesterday evening was much better than the molecule, but that's different. But my catalyst is recyclable.
Thank you.
Thank you very much. Have you ever tried to produce composite with your thermoset resin?
Yeah, I expected this. I saw your talk, so I expect this question from you. Yes, you don't want to know how many. At the moment, actually, we are trying to use the recycled rubber. Sorry. Many materials are brittle, especially bio-based plastics are brittle. Polylactic acid, you name it, all polydroxycarbonates. One way to correct for brittleness, to make a material tough, is to add the rubber. No, this is a solution to a problem which is as old as me. It's a 50-year-old solution, I'm not joking. But so far, has not been used because rubber are expensive. If you take polypropylene, which is €1 a kilo, and you have to add the rubber to make it impact resistant, which is €2.5 a kilo, then your price goes up, right? So that's the reason. It's called rubber toughening. My rubber is not €2.5 a kilo. My rubber is less than €1 a kilo. So yes, we have a lot of projects. At the moment, we have one in which we say green meets circular, which take biopolymers, which are very nice but brittle, and we add recycled rubber to make them tough. So there is a lot of work to be done, and that's the reason why I need at least 20 students a year. At the moment, we have a project with Philips. They're trying actually to use this rubber in percentages around 10 or 20% to make, they have the ambition to make a new coffee machine which is completely from recycled materials. So the answer is yes. I overstayed my welcome. A little bit longer than expected, sorry for that. I think if there are more questions, I will be around the whole day. I will be there around for dinner. You can pay me a beer and ask me questions. No, no.
Francesco, thank you again for your impressive talk. So please, thank you to all the audience. We need to start with the presentation. The next chair, okay? Please.
So good morning to everyone. Now we will start with a new session for today. The second year PhD students will show them presentation. And I think that we can start from the first. That should be Nicoletta Baglieri with a talk based on block copolymer self-assembly via static and dynamic solvent vapor annealing. So the stage is yours. So Nicoletta, the stage is yours.
Thank you for your introduction. So good morning, everyone. Today I want to show you our results obtained so far about this study on self-assembly of block copolymers via both static and dynamic self-assembly. So probably someone yesterday also talked about block copolymers, so a brief reminder about the fact that they are macromolecules constituted by two different polymeric chains covalently bonded, and so they have the tendency to self-assemble in nanostructures, and by the controlling the polymer ratio, the polymer weight, and the presence or not of a functionalization layer, we can in principle control morphology, dimensions, and orientation of the final structures. And after having a polymeric mask, we can also have an inorganic replica of this mask through different kind of infiltration. So in my work, our first approach was focusing on the strategies of having the metallic infiltration of these polymeric masks through a liquid phase infiltration of gold in principle, and then studying how different polymer removal techniques can affect the final structures. In this case, we observed how different plasma gases, oxygen or argon, can have an influence on the final morphology and structures inside the lamellar. And what we observed using a static solvent vapor annealing, that is the step in the process workflow that guide the assembling of the nanomorphologies. So we used first a static setup that is As you can see from the image on the right, bottom right, it's just an handmade setup with an acetone reservoir that is the solvent evaporating inside a bigger beaker that is closed to form a chamber. And actually, we observed that varying the annealing time, we can have different ordering degree of these lamellar block copolymers. We quantified this order using the correlation length, and we observed a 3 steps evolution until a sort of plateau, so a saturation of the process. But this approach has had many problems. First of all, we had no control on the ambient conditions, and so the evaporation rate of the solvent inside the chamber, and so also reproducibility was very poor. So our first solution, I mean, we are still working on that. We tried with a cyclic dynamic solvent vapor annealing setup, where we could have a fine control on conditions that influence the solvent evaporation, control on the solvent flux inside the specimen chamber, and also we could cycling the swelling and the swelling of the polymer on the substrate, monitoring it in real time with an interferometer. And so we could also perform different kind of experiments varying different parameters. In this case, we choose to infiltrate the final structures with alumina, because the process using an ALD approach is more stable, so we could focus on checking the morphology coming from polymers. And this is the whole set of first samples, and we can see how different parameters can influence the final morphology in terms of solvent flux varying from 50 to 200 milliliters per minute. And in some cases, we also were able to observe first step of organization in terms of hexagonally packed cylinders. We can also observe how different annealing time can affect the final structures, and in this case we can see that also with low annealing time we already have some structured morphologies, and finally the number of swelling cycles. But what was surprising for us is that for the strategy adopted, we could expect lamellar structures perpendicular to the substrate. Instead, we obtained either cylinders perpendicular to the substrates, or for example, the third row, we are hypothesizing that these are just lamellar structure but parallel to the substrate, so we can just see a flat surface. And so we are just now working on why this happened. And as probably you know, in principle, just the way the volume fraction of one polymer with respect to the other one should be responsible for the final morphology. But this is for sure true if you have a bulk material. But we are talking about thin film materials. In this case, the kinetic inside the block copolymers can change. In particular, what we found in literature, and seems to be a good explanation also for our case, is that when you use a solvent, in this case toluene, that is selective just for one or two polymer block, it is selectively absorbed by one of the two blocks when we are spin coating the polymeric solution on the substrate. And so there is an interaction between this absorbed solvent and the polymeric chains. In this case, for example, polystyrene chains have the tendency to interpenetrate, and so starting from the micelle morphology, initial micelle morphology, we have body cubic centered lattice of micelle, and then both polystyrene and P2BP undergo vitrification in a cylinder morphology, and so that they are, the polymeric chains do not have anymore the chain mobility needed to self-assemble in lamellar structures. So we have two morphological transitions, but not enough to have the final morphology we could expect. So we tried, and this is our last step at the moment, to investigate also how different film thickness could affect the final morphology, or the presence of a random copolymer functionalization layer. But we observed that none of these different parameters really affected the final morphologies that are still very similar to cylinder ones. And so this could be an evidence of the fact that once the polymers undergo vitrification and they are immobilized inside in their morphology, they cannot have more evolution in terms of morphology. But this is still under study in our research. And so we, of course, could conclude that there is a good reproducibility of these nanostructures, but even if they are not what we expected. And we confirmed that also spin coating is a crucial step in the block copolymer self-assembly. And so we need to further investigate the ordering transitions of these structures and how also the post-process treatment could affect the metallic structures. And in my PhD project, I plan also to have an electrical characterization of these metallic structures and geometrical characterization and chemical composition quantification by an hybrid metrology approach. So this is all. Thank you.
So thank you, Nicoletta, for your kind presentation. There is any question for Nicoletta? Don't be shy, this is the first talk of today. No one, so I have just a curiosity for you. Which are the thickness of your samples and in which way you measure them?
So the thickness was...
Maybe, I don't catch it.
Is more or less because you prepare the polymeric solution with a defined concentration of the polymer, of course. But then when you have the spin coating step, you are not sure that all samples have exactly the same thickness. And then it's just an ellipsometer measurement of the...
You have a distribution of, you can say.
Yeah, when you just spin coat, the polymer is a flat surface, so also with a look you can more or less say if it's quite homogeneous on the surface, but yeah, if you analyze your model by the ellipsometer measurement, you can have some hints about the distribution.
Thank you so much again, Nicoletta, for your presentation. So we will go with Andrea Lanfranchi with polymer photonics in thermal management.
Okay, thanks Simone for the kind introduction, and good morning everyone. Today I'm going to try to tell you some hints about the use of polymer photonics in thermal management applications. Maybe some of you have recognized the background image for my title slide. It's from a movie, from a late 70s movie, which is called Alien from Ridley Scott. And if you remember, the tagline of the movie was, "In space, no one can hear you scream." That's true, you know, because in space, there is no air. It's all empty, and so sound cannot propagate. Also, space is extremely vast, almost infinite, and extremely cold. It's between 2 and 3 Kelvin. So is it any way to harness this cold reservoir? All that separates us from the void is just our atmosphere, just a few tens of kilometers of air. It's not even noticeable if you look at the figure of the Earth. You just see the clouds, which are so small. And if you check the transmittance spectrum of the atmosphere, you will get something like this. There are some regions in which the atmosphere is essentially transparent. Which is the pointer? I don't know. This one? This one. In particular, one of these is called the main transparency window between 8 and 13 micrometers. All radiation through that window will be transmitted directly through the atmosphere into space or to Earth, depending on the provenience. So, why the transparency window is that interesting? Because if you check you know that all bodies emits thermal radiation, electromagnetic radiation, due to Planck's law. The shape of the emission depends on both the wavelength and the temperature. And for a body at ambient temperature, something like 300 Kelvin, you will see that the emission is this kind of bell-shaped curve, which is centered at the transparency window. Now, this is an approximation, because there is no such thing as a black body here on Earth. Everything will be slightly different, and this curve will be modulated by a parameter, which is called the emissivity of the body, and depends on the wavelength. But to use this, we have to understand a key factor, that the emissivity is the same of the absorptivity due to Kirchhoff's law. So, a highly absorbing material is also a highly emissive material. This means that, for example, a polymer such as cellulose acetate, which has all these nice absorption peaks into the medium infrared, will also be a really good emitter in the same spectral region in correspondence of these peaks. Now, when a body emits thermal radiation, it also receives thermal radiation from the external environment. And the final energy balance will be given by Stefan Boltzmann law. So it depends on the fourth powers of both the temperature of the body and the temperature of the exterior. But now you may think, what happens if an object emits thermal radiation, for example, cellulose acetate or this fluoropolymer from Solvay Specialty Polymers, in the transparency window? Well, vibrational modes that emits in the transparency window will send energy directly into space without receiving nothing in return, because the space is too cold to give back energy. So, we will attain radiative cooling, a net energy flux from the body into the universe. We are exploiting this cold reservoir to cool down objects. Of course, there are some vibrational modes more interesting than others, such as COC bonds, CC bonds, and CF bonds, because they emit in the right spectral region. Now, to actually measure this phenomenon is not that easy, because there is no setup that you can buy. So we tried to build one, and when I say build, I mean literally with a saw and a ruler. And I built this setup. And the idea is very simple. You put two samples in these two chambers, and you measure their temperature with two thermocouples. And of course, the setup is not randomly designed. It is made out of highly insulating polystyrene foam, because we want to shield from parasitic conduction, otherwise you can't see the radiative effects. And then we need to provide it with a convection shield, which is a thin layer of polyethylene. If you check the absorption spectrum of polyethylene, you see that it has no absorptions in the transparency window. Therefore, all the radiation can pass through it. And also, the same can be seen if you check with the thermal camera image the setup, because you can see the samples inside the chambers through the polyethylene shield. With this setup, we made just a few measurements. The work is really preliminary, so I just report you two measurements. We compared an aluminum sheet with a mirror bought on Amazon, made out of aluminum and covered by polyethylene terephthalate. Basically, you can see that with the setup, if you just put them below the sky, the temperature drops below the temperature of the air. For the aluminum sheet, up to this value. For the aluminum PET mirror, a little bit more. The drop is a little bit more because polyethylene terephthalate is more emissive than aluminum. Therefore, the emission is more and the net cooling is higher. This is called subambient cooling, radiative cooling. We also try to use the Solvay specialty polymer for this. We just added it to the PET mirror that we used in the first experiment, and we've seen a really slight improvement of the radiative cooling capacity. Now, of course, as I said, these are really preliminary results. Therefore, I don't really have any conclusion for you, but just a future perspective. So the idea is the integration of photonics into this kind of stuff. So we want to be able to both reflect light, reflect sunlight, and emit light, and emit electromagnetic radiation in transparency window. This way, we could be able to attain subambient cooling also under sunlight. To do so, we want to exploit our structures. Andrea told you something about them yesterday. Essentially, they are photonic structures that are able to reflect light in particular manners. Ideally, you can make a perfect reflector for all the sunlight for all sunlight, which also emits because can be made out of polymers. So with this, I thank all my group, and also I thank the Associazione Italiana Macromolecole and the family of Doriana Cittarelli for sponsoring my participation to this conference. And also I thank the audience for your attention.
Thank you, Andrea, for the nice presentation. I think that some one of you have questions for Andrea. No, but I have just two curiosity to ask you about the experimental setup. That is an handmade setup. I want to ask you if clouds and the difference in the light suns affect your measurements, and in which way you can control this parameter. It is difficult.
Yeah, thanks for the question. Yeah, these measurements are really difficult to perform because, first of all, the subambient cooling at the moment, we just obtain it without sunlight. Because to obtain subambient cooling under sunlight is extremely difficult. You need to integrate a really, really, really good reflector with a really, really good emitter. Just to say, you need to reflect about 96% of total solar radiation if you want to see the ESA effect under sunlight. Basically, only silver mirror can do this at the moment. And of course, the performances will depend on where and when you do the measurement. Because if the day is cloudy, there is basically a water column over your setup. Water is highly absorbing, and therefore the atmosphere is much less transparent. This way the cooling is reduced. What I presented before, the transmission of the atmosphere, was a simulation made with some softwares. But there are a lot of parameters that affect that transmission. That was just a general idea of what's the actual transmission of the atmosphere. So yes, it's extremely difficult. It depends on the day. It's really difficult to reproduce because every day is different. As the season progresses, the atmospheric composition change. So it's a mess. It's really a mess.
Okay. So if there are no questions for Andrea, we will thank you for your presentation again. And then we will go with the next speaker, should be Edoardo Miravalle, with a talk called Recycling Abilities of Optical Transparent Bio-Based Polyurethane Networks. So the stage is yours.
Thanks. Thanks for the presentation, and I will talk about some results of my PhD project, so the recycling of a novel bio-based polyurethane network. In this presentation, I will talk briefly about plastic production and the fate, then I will talk about the theory that's behind the reprocessing process of some kinds of thermosets. And then I will talk about synthesis, reprocessing, and then characterization of the novel bio-based polyurethane network that our group synthesized. And then I will do some conclusions. So starting, I want to highlight the situation of plastic production on, globally and in the European countries. As we can see, globally, the production of plastic in 2021 reached 308 million tons, and in European countries, 57 million tons. As we can see in both scenarios, polyurethanes counts up for 5.5% of all produced plastics, placing this polymer as the sixth produced polymer, but most importantly is the first thermoset produced around all the polymers. So it's important to know the fate of the plastic, of this kind of plastic that occurs at the end of life. Several processes are actuated, but nowadays mainly two are used due to the recalcitrant structure of this polymer. And in fact, the main used are landfilling and energy recovery. But in the recent years, a new strategy aroused is mechanical recycling, because it's thought that this mechanical recycling can be a new path for real recycling and maybe upcycling of this kind of materials. The recycling of this kind of thermoset has basis in the covalent adaptable network theory. For this theory, some kinds of thermoset can exhibit dynamicity under the application of certain stimuli, such as temperature, pressure, variation of pH, radiation with light. During the application of the stimuli, the bonds forming the thermoset can break up and then reform, permitting a rearrangement of the material itself. The mechanism which these events occurs can be associative or dissociative. That's the difference between the two mechanisms, the timing of the breaking up and the reforming the bonds, as reported in the scheme for polyurethane exchange. But what's important for this mechanism is that during the rearrangement of the thermoset of the network, there can be a maintenance of some properties such as cross-link density. So this mechanism is suitable for different applications such the creation of materials, self-welding or self-healing materials, but also for recycling. So talking about our project, a colleague of mine, Gabriele Viada, synthesized a new material, a new bio-based polyurethane, using both bio-based isocyanate and polyols, using a canonic catalyst, obtaining a highly transparent polyurethane bio-based that can be suitable for future optoelectronic applications. Regarding the reprocessing process, we applied for this material a thermomechanical process that's the most used for this kind of thermosets. It's easy and fast, it can be potentially scalable. It consists in three phases, in pulverizing, compacting, and then heating up the samples. So we have done it for our polymer. We finally ground it. We hot pressed it at 170 degrees for 45 minutes and under 2 tons of pressure. And we obtained the films after the reprocessing that can be reprocessed up to 3 times. As we can observe, a slight yellowing occurs during the reprocessing processes. But analyzing the materials, we observed in the infrared spectra that no change in the spectra can be observed during the reprocessing of the materials. No signs of oxidation can be observed, and so we can say that no real structural variation can be observed during the reprocessing of the samples. Also, observing the thermal analysis, we observed a slight decrease in the thermal stability of the material, but only after the first reprocessing process. For the subsequent ones, the thermal stability is stable. And also, we observed no variation in TG. That's interesting. And, but what's more interesting for these kinds of polymers is that there is a increasing of the tensile properties in the more the materials is reprocessed. As we can observe in green, the third reprocessed material, respect the pristine one, we observe that there is an increase in both stress at break and strain at break, and no variation in modulus can be observed. So this process can be a real path for real upcycling of this material. To have further insight of what's going on in this reprocessing process, we also carried out a rheological analysis, and so we observed an increase in storage modulus for the third reprocessed material respect to the pristine one. With this parameter, we could observe that there is an increase in cross-link density and a decrease in molecular weight between the cross-links. And that's, these parameters can explain why the tensile properties change during the reprocessing of the samples. We also observed that the third reprocessed sample has a lower relaxation time with respect to the pristine one. And so we can say that cross-link density has an important role in the relaxation times and dynamics exchange of this material. So, concluding, we have reprocessed a novel bio-based thermoset polyurethane up to 3 times with no real variation of the structure. We observed an increase in values of tensile properties, an increase in modulus and a variation in cross-link density. And obviously, further studies have to be carried out to assess how the reprocessing processes affect the structure of the polymer during the reprocessing processes, but we think that this path can be a real upcycling path, and we hope to extend this mechanism to other types of polyurethanes, and that's all. I'm available for question if you want.
Thank you, Eduardo, for the really nice presentation. Someone of you have question for Eduardo? Yes, there is one from there.
Thank you, Eduardo, for your kind of presentation. Just a curiosity, have you ever estimated the cost of your recycling process?
Thanks for the question, interesting. Now we are in the laboratory level, so we have did not estimate the cost. I know that I've presented like such conditions. It's not really appealing for industry because 170 degrees and 45 minutes are quite a lot. But we have to say that this polymer, it's a novel bio-based polymer. It's a little bit more complicated to reprocess this material respect other types of materials. In the literature, you can find for canonic polyurethanes like tempistic of minutes, 1 to 5 minutes, and temperature that are lower than 170 degrees. So for this, I said that that's potentially scalable, but we have to check it out.
Thank you.
There is another one there.
Thank you for your nice presentation. I wanted just to ask if the optical properties, so this transparency, remains when the material is stretched. When the material is stretched, yes, when you subject it to mechanical stress. The optical properties
thanks. Thanks for the question. We have not checked it out because it's not the materials. It's created for another purpose, a static purpose. We don't think that this material will be stretched out during the use because maybe it will be used like a coating or whatever. So we have not checked out this aspect, but it's interesting, and maybe we could check it out. Thanks.
Thank you.
So, thank you, Eduardo, again.
Thanks.
And we will go with the next speaker. That will be Carlos Pavon with tanning dispersity of polymer brushes to modulate their interfacial properties. So the stage is yours, Carlos.
Good morning to everyone. Today I would like to present you my work about how sidechain dispersity of these polymer brushes influences the interfacial properties. So modulating the structural parameters of polymer brushes, such as grafting density, molar mass, topology, or dispersity, represents a major factor by influencing these interfacial properties, such as lubricity, biopassivity, adhesion, friction, or steric stabilization. In this work, we focused on dispersity, especially side chain dispersity, since limited studies have been addressed to it. So, not only maintain dispersity of these polymer brushes, but also this side chain dispersity can influence these interfacial properties of these polymer brushes. So the main objective of this work is to tune this polyoligocylene glycol methyl ether methacrylate side chain dispersity to modulate the physicochemical properties of these polymer brushes. So the corresponding monomer is commercially available, and it has an average of molecular weight around 500 Dalton. Indeed, by a simple thin layer chromatography, you can already see these different discrete molecular weights. In addition, from 2 to 15 repeating units of this oligocylene glycol can be found in the mixture. By applying by UPLC, you can observe the distribution of the discrete molecular weights, and in order to modulate the side chain dispersity, we can perform a flash chromatography in order to separate the most abundant discrete molecular weight, that in this case is the octamer, whose molecular weight is 452 Dalton. So for the fabrication of these bioECMA brushes, we followed two different strategies. The first one, grafting 2 approach by applying ATRP arget, in which we generate this initiator with an anchor containing this disulfide in order to assemble the polymer ligands on gold substrates to proceed to their characterization. And then the second strategy is the grafting from by applying surface-initiated photo-ATRP, in which we attach the initiator on silica wafers and then proceed to the polymerization. But before the assembly of these polymer ligands, we characterize them by proton NMR to follow the conversion, and then by gel permeation chromatography to measure molecular weight and dispersity. Since in this work we wanted to focus on this side chain dispersity, we maintain constant the main chain dispersity and the molecular weights of the two different ligands. Then, once these polymers are attached on the cold surfaces, we proceed to perform several wettability studies. First of all, to calculate this water content, which represents how much water these polymers can absorb. But before, we needed to measure the dry thickness by ellipsometry, and we obtained around 2 nanometers for the grafting to approach and 60 nanometers for the grafting from approach. Then we proceed to measure this hydrated mass, in which we used quartz crystal microbalance and dissipation for the grafting to and ellipsometry in liquid for the grafting from. Regarding QCMD, we deposited these polymers on quartz piezoelectric sensors, in which they have a determined frequency. Indeed, frequency is inversely proportional to the mass. So when we deposited these polymers on the system polymer plus water, this frequency changes over the time. So in here we made a baseline with water, then we deposited the polymers on these sensors, and finally we injected water. So the difference between the baseline and this position, we will get directly the hydrated mass. With this, we can calculate the water content, in which you can observe in here how the discrete side chain polymer brushes is more, has a water content higher than the heterogeneous analog. So it means that the discrete side chains polymer is more hydrated. This can also be confirmed by these contact angle measurements, in which we recorded the static and the dynamic. And in here you can see how the discrete side chain polymer brushes has a lower angle. Finally, we proceed to perform several nanomechanical and nanotribological studies, first of all by addition test conducted by colloidal probe atomic force microscopy. In here, we attach a silica colloid coated with gold, and we attach it on a cantilever, and then we assemble the polymers. This procedure was followed for the grafting 2 approach. While for the grafting from approach, we attach directly the silica colloid on the cantilever without brushes. So for the approaching, we measure the repulsion while compressing this probe to the substrate. So in the graphs, you can already observe how the discrete side chain polymers, there's a higher repulsion compared to the heterogeneous analog. Then we measure this retraction, which measures the addition properties of each polymer. So in here, you can see how the polydisperse side chain is more sticky than the discrete side chain. And in here, for the grafting from approach, is more highlighted since the thickness is higher. And then we measure also some friction properties conducted by colloidal probe lateral force microscopy, in which we measure this lateral deformation of the cantilever. So the graphs show this friction force versus applied load, and the slope, which represents the coefficient of friction, is much more emphasized for the polydisperse side chain compared to the discrete ones. So it means that the discrete ones has more lubricity compared to the other polymer brush. And this can also be confirmed by this grafting from approach. So with this, I would like to conclude by emphasizing the main points of the work. So we were able to modulate the side chain dispersity by separating the discrete molecular weights. And then we can demonstrate how the monodisperse oligoethylene glycol side chains influences the interfacial properties by preventing from van der Waals or hydrophobic interactions and favoring this water molecules association. Then we also observed how the lubricity increases and how the addition decreases. And finally, I would like to thank my group, all the collaborators, and all of you for paying attention. Thank you.
So, thank you, Carlos, for the really nice presentation. There is any question for Carlos? Yes, two. 3.
Hi Carlos, thank you for a nice presentation. I just have a curiosity, maybe I don't get during the presentation. When you separate your molecular weight of the monomer, why you choose the exact that you use and not another one, for example, of molecular weights, I mean?
So we choose basically the most abundant just to have a more representative results basically. And also like we have this mixture of, one moment I show you the, okay. So in here you have this distribution, so we choose directly the most abundant. Also because by applying this flash chromatography, which maybe here, for example, with starting with 100 grams, we can only get like a few grams. So with the most abundant is easier, let's say.
Okay, thank you.
Thanks for your presentation. Just a curiosity. I know PEGMA is a thermo-responsive polymer, so you don't mention critical solution temperature, but I know it has. So in the last slide, you only say water molecule association. So I was wondering if you checked the variation of the critical temperature basing on the variation of the chain length, or it's something you don't need.
Okay, thank you for your question. So yes, it's true that this polymers is thermoresponsive, and we checked, but we didn't see any difference between these polydisperse and monodisperse side chain. So we just proceed with other techniques in which we highlighted this difference.
Hi, Carlos. Thank you for the nice talk. Also, mine is a curiosity related, for example, with the first question. You test the characteristic of your final product. Do you know which application could be related to the result that you obtain? And if you think that, of course, with other molecular weight selected for the side chains, you could obtain different properties that could be related to different applications.
Okay, thank you for your question. So first of all, I mean the main application would be like to generate this library in which, depending on the future applications that you are interested in, you can choose which polymer use. And also, for example, it's also well known that this dispersity can favor the stabilization of particles, for example, and also can depend on the protein absorption, which is also interesting. And related to the other question, indeed, here we are comparing not the molecular weight itself, just the dispersity of this main chain or side chain dispersity of the polymers.
So we are a little bit in late, so thank you, Carlos, again for your nice presentation. And we will go with Mariangela Rea with rheologic assessment of enzymatically cross-linked tyrosine functionalized alginate hydrogels for biomedical application. Mariangela, the stage is yours.
Thank you, Simone, for your presentation. Good morning, everyone. So I would like to start with a quick introduction about the polymer hydrogels. They are basically polymeric networks which have the ability to hold water within the spaces that are available among the polymeric chains. And their particular properties make them suitable for a wide range of biomedical applications, including tissue engineering, 3D cell cultures, and drug delivery. Focusing on the cross-linking points, we know that we can have hydrogels that can be chemically cross-linked or physically cross-linked, depending on the nature of the bonds. So we can have covalent or non-covalent interactions. And in the first case, we have that our material will be characterized by a more reliable shape stability and memory. Among the different materials which can be used for these applications, alginate, which is a natural polysaccharide, is particularly interesting because of its high stiffness, low toxicity, and easy availability. But it can be just physically cross-linked in the presence of calcium ions. So if we want to chemical cross-link alginate, we should modify it. And in literature, we have a lot of results, a lot of works reporting the synthesis of methacrylate alginate, which can be photocross-linked through a process that is very characterized by high speed, precision, and the ability to define locally the cross-linking density, but still from some drawbacks like the poor light penetration and potential cell damage. So we thought that the enzymatic cross-linking could be an interesting alternative to obtain covalent cross-linked alginate in exploiting a reaction that is self-friendly, highly selective, and can be suitable also for injectable hydrogels. So our idea was to synthesize this tyrosine-modified alginate through this reaction that is an EDC-NHS coupling, starting from alginate and tyramine, and then to exploit the enzymatic cross-linking operated by the horseradish peroxidase enzyme, which is a single-chain alpha-type hemoprotein, which in the presence of hydrogen peroxide can conjugate phenol and anidine derivatives. So after the synthesis, the material was purified and lyophilized, and we passed to the hydrogel preparation. In this case, we prepared an hydrogel starting from a sample with a degree of substitution equal to 17.9%, and we dissolved it in a phosphate buffer solution with a pH equal to 6, which is the pH at which the enzyme have its maximum activity, and in hydrogen peroxide with a concentration equal to 40 millimolar. And the hydrogel was prepared with the Luer-Lock syringe system. And on the other syringe, what we had was our enzyme with a concentration equal to 200 units per milliliter. The aim of the work was to characterize this material from a rheological point of view, considering the 3D bioprinting application. So we, in this work, I reported mainly two tests, which are the time sweep that can help to monitor the gelation kinetics and to understand which would be the final equilibrium storage modulus of the material, and to understand which is the time for the cross-linking to happen. And then we have the amplitude sweep that can help us to characterize the material after the cross-linking is completed. So, starting from the time sweep test, basically we can monitor how the storage modulus and the loss modulus change over time. And here there are two samples characterized by the same ratio between the enzyme and the hydrogen peroxide, which was previously optimized, and two different concentrations. And we can see that passing from 3% concentration to 8%, we're able to obtain much higher values of the storage modulus, and also to monitor the gelation kinetics. More specifically, we pass from 10 Pascal of storage modulus to 1057 Pascal, and the crossover point is observed after about 7 minutes. But to study more in detail the gelation of our material, we calculated the first derivative of the storage modulus curve, which is represented by the red curve on the right. And here we can see that the peak that is appearing is actually underlining the interval of time in which we have the highest changes in the value of the storage modulus. So we can say that we can take the width of the peak as our time interval for the enzymatic cross-linking to happen, which is around 17 minutes. But also, what is interesting is that after 30 minutes, we actually did not reach a final equilibrium storage modulus. Indeed, from this simple calculation with the first derivative, we can see that the modulus is increasing again. So, and this was confirmed by the amplitude sweep test, which was performed after 1 hour of cross-linking instead of 30 minutes. And here we can see that we obtained much higher values of storage modulus, which are around 18,000 Pascal. And also we can observe that the material is gel-like, since the storage modulus is higher in value than the loss modulus. And finally, which is very interesting from this result, is that we calculated the tan delta value, which is given by the ratio between the loss modulus and the storage modulus. And we calculated it inside the linear viscoelastic range. And it is equal to 0.24. And this is particularly interesting and useful because we know that for materials which have to be employed for the 3D bioprinting application, this value should be higher than 0.22 in order to have a material which is easily extrudable through the nozzle. And also, morphological analysis was carried out through the scanning electron microscopy, and this was a further confirmation of the fact that the cross-linking was successfully obtained, since we can see the appearance of pores within the matrix of the hydrogel, and this is essential for the cells uptake, for the cells encapsulation, and for the nutrients uptake. Finally, the last study regards which is the effect of the degree of substitution of tyrosine moieties within the alginate chains. And here we can see 3 samples characterized respectively by 17.9% degree of substitution, 34.4%, and 82.4%. And you can observe that by increasing the degree of substitution, we have lower final values of storage modulus after 1 hour, and also the gelation is much slower. And we ascribe this result to the fact that maybe a rapid local gelation happens as soon as the hydrogen peroxide comes in contact with the enzyme and the tyrosine moieties, preventing the homogeneous diffusion of our substrate within the matrix of the gel, slowing down this process. So in conclusion, we can say that with this system, we successfully obtained the enzymatic cross-linking of alginate, and that by tuning the polymer concentration and the time of gelation, we can obtain different final values of elastic modulus addressing different tissues and organs in vivo, and that the higher is the degree of substitution, the slower will be the gelation. So the next step will involve the study of samples with a lower degree of substitution, which showed the widest range of obtainable final values, and of course, to complete the rheological characterization for the 3D bioprinting application. I would like to thank the organizing committee and my supervisor, and also Professor Richard Gross, who is contributing to this project, and you for your attention.
Thank you, Mariangela, for the really interesting presentation. We have time only for one question for Mariangela. Yes.
Hi, Mariangela. Thank you for a nice presentation. I just would like to know if in your studies that you think you will do in the future, you will study also how the concentration of your enzyme can influence the rheological properties of the hydrogel, and you think, for example, if the crossover points can have some changes.
Thank you for the question. Yes, we started from this concentration based on literature research, but of course it has an influence, and the highest is the concentration of the hydrogel, of the enzyme, the higher will be the speed of the enzymatic cross-linking. So for now we were focusing on this concentration because the obtained results are already good for the application, but of course then we will study also the different concentrations of the enzyme.
So again, thank you, Mariangela. And we will go on with Lorenzo Rocchi, who show us polymer glass transformation kinetics. The stage is yours.
Good morning, everybody. My name is Lorenzo Gusto Rocchi. I'm a PhD student in Sapienza University of Rome, but currently I'm also a visiting student in the Material Physics Center based in San Sebastian, the Spanish Basque Country. My research topic is polymer glasses, and the title of my today's presentation is Polymer Glass Metal Transformation Kinetics. Before starting my talk, I prepared this slide in which I show you the main topics I will discuss today. I will start with some theoretical background on vitrification techniques and aging and de-aging phenomena in glasses. Then I will continue with the experimental procedure and the results of the study, and at the end I will finish with the conclusions. So, glasses are amorphous solids that can be produced by different techniques. In particular, supercooling, which involves the rapid cooling of a molten mass, so it has no time to crystallize, is one of the most popular ways of producing polymer glasses. From a thermodynamic point of view, the relationship of thermodynamics properties such as entropy, enthalpy, and volume as regards to the temperature is shown on the slide. The positive slope of the liquid equilibrium stands that regardless the cooling rate, when the liquid is cooled down, molecular motion and therefore conformational exploration are both reduced. But if we cool down a liquid slowly, the material has enough time to explore different conformations, reaching the minimum in the free energy and organizing in an ordered crystalline structure. But if the liquid is cooled down fast, crystallization can be avoided. Supercooled liquid can be achieved, and at the glass transition temperature, the material have no time to equilibrate in the variable time imposed by the cooling rate. So the system exits from the equilibrium, reaching the glassy state. From a classical point of view, this is governed by a super-Arrhenius process known as alpha relaxation. When a system is forced out of the equilibrium, like the glassy state, it spontaneously tries to evolve to return to the equilibrium condition. For glasses, this is known as physical aging. If we hit a glass that had no time to age, on the Cp, that's the first derivative of the enthalpy, we'll see a classical sigmoid. But if we hit a glass that had some time to age, we'll see a peak, known as overshoot. And if we hit a glass that had more time to age, reaching, for example, the liquid equilibrium, the peak will be higher. So by the time, this peak increases, and it reaches a plateau at the equilibrium time. By integrating the peak, we can also calculate the enthalpy loss or recovery during the scan. We just said that glass that had completely aged had this trend. But what happened if we hit this glass to a new temperature, higher than the aging temperature, but lower than the TG? In this case, the system has a lower enthalpy content. So we try to evolve to equilibrium again, increasing the enthalpy content. So by hitting scan, we will also see the enthalpy peak, the overshoot, but lower in intensity. And at equilibrium will be the lowest. So aging and de-aging are essentially two approaches to equilibrium from two different parts. These have been widely studied by Kovacs in the 1960s, and it's known as Kovacs' asymmetric approach to equilibrium, because we arrive to the same equilibrium with different kinetics. Even if the equilibration time, the time in which we arrive to zero in this case, it has to be equal for aging and de-aging. So, experimental procedure. I use flash scanning calorimetry, a colorimetric technique able to span up to 100 calories per second. The sample was atactic polyfluorochlorestyrene, analyzed with a heating scan of 1,000 calories per second and a mass of 137 nanograms. I studied aging and de-aging with the temperature programs shown on the slide. I will show here the results of aging and de-aging at the same temperature, 404 Kelvin. In the case of aging, on the left, we'll see the overshoot increasing, reaching the equilibrium, the plateau, in 5.5 seconds. On the other hand, on the right, we have the aging. We start from a high peak, the deep glass, and the peak lowers the intensity, reaching the same equilibrium, but in higher times, 30 seconds. So the asymmetric approach of Kovacs exists. For understanding better these differences in the equilibration time, I will show you the enthalpic recovery during the aging. So the enthalpy in different experiments conducted from 390 to 412 Kelvin, it always increase, reaching the plateau in the full dot. If we plot my results on an Arrhenius plot, we'll see that for low temperatures that are on the right, because we have the inverse of temperature, there is splitting from the alpha relaxation taken by literature, by Simone Napolitano, by experiments of dielectric spectroscopy, and confirmed by us by the stars that it's not really clear to see with modulated flash scanning calorimetry. This splitting is also clear during the de-aging. I showed you the asymmetric approach for 404 Kelvin. We can see the insurgent of equilibrium at the same enthalpy, but the equilibration time is different, as is different the stretching of the kinetics to reach the equilibrium. So the reds are the aging experiment. He has a divergence from the expected values, but a mild activation than the aging itself. So, for conclusion, this study indicates that the process of eliminating thermal history from a deep age glass takes different time than expected. And the magnitude and the direction of the deviation of this phenomenon depends on the temperature analyzed. So I finished. I just want to thank you, all of you, for the kind attention, and my research group in the Sapienza and the Material Physics Center. Thank you.
Thank you, Lorenzo, for the really interesting presentation. There is only one question that we can ask to Lorenzo. In any case, I will go on. Just a curiosity for you is if you are able to use this cancellation of thermal aging in some applications.
That's a hard question. I would say that this research, like all my researchers, are science for the science sake, like art for the art's sake. Basic science research, the difference in 30 or 5.5 seconds in the aging is not industrially applicable. So just understanding the mechanism by which a glass, the age or age, all lose all the enthalpy and volumetric stuff. Maybe one day they will use it, but for now, no, just basic.
Thank you again, Lorenzo, for the presentation. So we will go on. The next speaker is Ruggero Rossi from the University of Florence that will talk So we will talk about liquid crystalline elastomers by 3D printing for photoresponsive actuators. Ruggero, the stage is yours.
Okay. Okay, thank you, Simone. I'd like to show you my results about ink development and printing of liquid crystalline elastomers for photoresponsive actuators. These are systems that can convert light energy into mechanical work thanks to the combining of the liquid crystal anisotropy and the mechanical properties of the elastomers. These systems find many applications, such the ones that Simone showed you yesterday, and also in the biomedics for the development of artificial muscles. In our group, we prepare liquid crystal elastomers strips that can respond to light by contracting and relaxing after we turn off the light. We can give the photoresponsivity by adding an azobenzene chromophore, and the directionality of the actuation is given by the alignment of the liquid crystals that we can give by infiltrating the liquid crystal mixture into a glass cell and then polymerizing, cross-linking the mixture with photocross-linking. This technique has some limits, such as the dimensions of the film we can obtain, the kind of alignments, and the kind of geometries that we can give to the material. Also, we need to automate this process, since the quality of the film is given by the operator, and every operator makes a different film. One solution can be the 3D printing of these materials, since we can give many different, we can program the dimensions, the geometries, and we can automate the process. So, through direct intruiting, we can give the alignment to the liquid crystals from the shear stress of the extrusion itself of the liquid crystals. So we can go from a polydomain state of the liquid crystal to a monodomain. We can align the liquid crystals on a molecular director N, and after the cross-linking of the material, we can stimulate the material with a temperature increase or light irradiation to obtain a contraction along the molecular director. So we can start from the ink synthesis. We use a liquid crystalline diacrylate to give the liquid crystalline properties, and a diethyl chain extender to obtain an oligomer, which is doped with an azoacrylate. So we obtain this azo oligomer, and we prepare three different inks with different dye quantities, and we saw how the increase in the dye quantity does not affect the molecular weight, and not so much also the polydispersity of the oligomer. We need this thiolene reaction to obtain an ink that has the right viscosity to be 3D printed. So we can also add inside the mixture a photoinitiator that will be needed for the photocross-linking. After the preparation of the ink, we can charge it on the printer, and we can start printing. You see, we have a UV crown mounted on the top of the syringe that gives an initial photocross-linking. We usually prepare simple strips, but we can also give different geometries, such as that honeycomb. After the printing, we need to post-cure the material to obtain a complete photocross-linking that we check from IR spectrum. So we can see how the typical signal from the double bond of the acrylate group is disappearing, so we know we have the photocross-linking. After this, you can see a polarized optical microscopy video of the film, and we can see the alignment of the liquid crystal from the change in birefrangency of the structure. We did some mechanical tests by DMA, stress strength test, and we see how the temperature change does not affect the mechanical properties, and also the dye quantity does not really affect the mechanical properties, but we can see the anisotropy of these materials, since the tests performed in the perpendicular direction of the printing give a bigger elastic modulus comparing to the parallel direction of the printing direction. Last, we perform some light attenuation. Initially, we just irradiate the material with green light to see if it responds to light, and we see we have a bending of the material and the relaxation after we turn off the light. Then we put these strips inside a micro LED system that should simulate the cardiac contracting. So we turn on a UV LED, we see a tension development, and after we turn it off, we see the relaxation of the material. And here we can see how the increase in the dye quantity increases the force developed. So, in conclusion, the quantity of dye does not affect the molecular weight and the polydispersity and the mechanical properties, but the more dye we put, we have a bigger force developed. In the future, we'd like to print new structures with new geometries and also use new dyes and try to use these inks for different printing techniques, which we already tried with electrospinning techniques. So thank you for the attention.
Thank you, Ruggero, for the really nice presentation. Do you have only one question for Ruggero? Yes, this is only one.
Hi, thank you for your presentation. Have you tried another 3D printing technique like resin 3D printing, or do you need this technique for the shear stress to align the polymer?
Yeah, if you try with something like resin printing, you don't give the shear stress that you need to align the liquid crystals, so you don't have the actuation, etc.
So it doesn't work like that.
So you need the direct int rising, for example. Yeah.
Thank you.
Thank you.
Thank you again, Ruggero. Next. Now we will start with the first year PhD students. We have a change in the timetable. Giulia will be the first, yes, but Niccolò Bini should be after the coffee break. So Giulia will, yes. Giulia will show us towards effective upcycling for polyolefins. Giulia, the stage is yours. Accendilo.
Okay. Good morning, everyone. My name is Giulia Bernagozzi, and I am going to talk to you about the research I am performing on upcycling, a novel strategy of mechanical recycling of polymer waste involving upgrading strategies to bring an additional value to the polymer waste stream, made in this case of polyolefins. In Europe in 2021, the plastic production reached almost 60 million tons. Polyolefins, including polyethylene and polypropylene, account for almost half of this European plastic production. More than 10 million tons of post-consumer plastics were sent to recycling, but only 5.5 million tons of post-consumer recycled plastics were used in new products and parts, account for almost 10% of the plastic conversion rate. So, numerous recycling processes have been established, but the ultimate fate of mechanically recovered plastics is still landfilling, incineration, or disposals because of the deterioration of the properties of the recovered materials. It is therefore necessary to improve the performances of recyclates and to bring them an additional value. And to achieve this, a strategy which emphasizes the exploration of the inherent value of the plastic waste has been developed, and we can talk about upcycling. In this work, upcycling of polyolefins were performed through reactive processing, and two case studies have been investigated. The first one on polypropylene and the second one on bottle caps. Now I will show you the results obtained with polypropylene. The material was subjected to reprocessed in a twin screw extruder up to 10 times in order to simulate the condition that the material undergone during its mechanical recycling. The material properties in terms of processabilities and changes in the molecular weight were monitored through rheological characterizations. You can see how the complex viscosities decrease when increasing the number of reprocessing cycles. Besides, the material reprocessed for a higher number of times shows a more pronounced Newtonian behavior. These two features indicate, as expected, a gradual decrease of the molecular weight. This last is confirmed by the trend of the Newtonian viscosities, calculated by fitting the experimental data with a model and plotting it with the number of cycles. It can be seen how there is a pronounced decrease of the Newtonian viscosity when passing from the virgin PP to the ones reprocessed 10 times. The same procedure was followed by introducing a commercial additive that should enhance the properties of recycled polyolefins. The additive was introduced in the polypropylene already subjected to one reprocessing cycle, aiming at simulate the condition that the material undergone during its pre-consumer or primary recycling. Also in this case, a decrease of the complex viscosity when increasing the number of reprocessing cycle is observed. And if we compared the Newtonian viscosity with the pristine PP, you can see how the introduction of the additive is beneficial, since we obtain a less pronounced decrease of the viscosity as a function of the number of the cycle. Similarly, we introduced the same additive at N9, therefore on PP already subjected to 9 reprocessing cycle, aiming to simulate the condition of post-consumer secondary recycling. The introduction of the additive also in this case results in increase of the complex viscosity, getting close to the results obtained for pristine PP. For what concerns the Newtonian viscosity, in this case we obtain a lower value with respect to the introduction of the additive at the first cycle, but a very increase with respect to pristine PP reprocessed 9 times. Moreover, the introduction of the additive results also in a lower decrease of viscosity, or lower rate of viscosity decrease over time. In order to better understand how this additive acts and induce modification of polypropylene macromolecular architecture, the material was processed in a mini extruder with a recirculating channel for 2 different times, 6 and 9 minutes. From the trend of the complex viscosity, you can see how the additive acts in 2 different ways. If keeping processing for 6 minutes, the introduction of the additive results in increase of the viscosity at low frequency, leading to the appearance of the so-called yield stress. While if we keep processing polypropylene and the additive for 9 minutes, it results in increasing the complex viscosity for the whole area of the Newtonian plateau. When looking at the relaxation spectrum, you can see how the material did not relax in the same times. If keeping processing for 9 minutes, the relaxation times are shifted toward lower values. When considering the introduction of the additive, the relaxation times are shifted toward higher values, never reaching the complete relaxation and even increasing over the range, the considered range. These features can be explained considering malstructuring phenomena given by the additive, such as cross-linking or maybe formation of long chain branches that could hinder the chain relaxation of the system. Now I want to show you little brief results on a real case study of recycled material that is bottle caps, a complex mix of polyethylene and polypropylene with traces of PET and polyamides. Also in this case, the material both and without the additive was processed in a twin screw extruder. And also in this case, we can see how the introduction of the additive was beneficial, since there is an increase of the complex viscosity and moreover an increase of the storage modulus at low frequencies. If we compare the mechanical properties of the 2 formulations, comparable elastic modulus and tensile strength values have been obtained, but the introduction of the additive results in a very high increase of elongation at break. So in conclusion, the commercial additive that we have considered allows increasing the viscosity and the molecular weight of polypropylene and bottle caps, paving the way for the effective upcycling of polyolefins. As future outlooks, the active mechanism of the additive is under investigation in order to understand if it acts like a chain extender or cross-linker, or maybe if it makes long chain branches. Moreover, after defining that, we will tune the microstructure of the recycled polyolefins in order to process them with different technologies. I would like to thank the committee organizing, my colleagues, and all of you for your kind attention.
Thank you, Giulia. Really nice presentation. Do you have questions for Giulia? We have time to do one question.
Thank you for your presentation. I have two curiosities. The first is the cost of the additive that you have used. And the second is if you have performed any morphological analysis on the polymer blends that you studied.
Thank you for your question. At all, so far, I don't know to say you the real price, since it's a collaboration with the firms. But for what concerns the morphological analysis, we have not yet carried out, but of course it's in our plans to do it, since we would like to understand what really happened to this system, since something happens, of course.
Thank you.
Well, thank you again, Giulia, for the really nice presentation. So I think that it's time to go to the coffee break, so we will go in the same spot as yesterday, and we will come back soon.
Ok, però io ho bisogno di istruzioni su come presentazione va e si vede lì.
Sì,
ok.
e basta, poi cambi le varie presentazioni e poi c'è il programma per i nomi. Si inizia da Niccolo Bini.
Niccolo Bini.
Doppio B. Metti in modalità presentazione. Metti in modalità presentazione se riesci.
Okay, so welcome back from the coffee break, everyone. And as you may have understood, I am the chair for this session. And so we will start with the presentation of Nicolò Bini, which will tell us something about optical and mechanical characterization of cellulose-based molded products. So Nicolò, the stage is yours, and the microphone is...
Okay, thank you, Giulia, for the nice introduction. I'm Nicolò Bini, a PhD student at the Material Engineering Department at the University of Bologna, and my PhD is in partnership with SACMI, a company based in Imola. As you can see on the screen, today I'm going to talk about optical and mechanical characterization of cellulose-based molded products. Nowadays, interest in cellulose is increasing due to the sensitivity on environmental causes. On one side, the EU introduced a new directive on single-use plastics, which prohibits the production of many objects made from plastics, such as straws, cutlery, and plates, since July 2021. And on one other side, many companies are trying to switch from oil-based to bio-based starting material, and cellulose seems to be one of the most good candidates. Both of these points are included in the new Green Deal initiatives, set of initiatives in order to obtain carbon neutrality by 2050 in Europe. In this framework, SACMI company, worldwide leader in the production of complete rigid lines for the production of rigid packaging, joined the task and started the development of a new dry molding technology, which uses a full metal isostatic mold for producing rigid packaging material out of cellulose. Cellulose was used, of course, because it's the most abundant biopolymer on Earth. It's extracted from plants together with hemicellulose and lignin. Of course, cellulose is renewable and recyclable. And being a natural polymer, his physical and chemical features depends on its source, which can be hardwood, like the cedus tree, or softwood, like conifers, such as pine. Depends on treatment intensity, such as the intensity of the deepness of the treatment we have. In fact, it's well known that the more you treat cellulose pulp, the less lignin content we have. So the aim of this project is to characterize cellulose both in the shape of raw material, raw cellulose pulp, and in the shape of final molded objects, so that to find a correlation between initial properties of the cellulose material, process parameter to apply, and final properties of the molded object. Firstly, we analyze some commercial cellulose by optical microscope, and these are the results for hardwood on the left and softwood on the right. As you can see, hardwood is shorter and thinner, while softwood is longer and thicker. And we have seen that's the difference between, for example, a toilet paper on the left and a banknote paper on the right. And we have seen that most of the companies that sell cellulose sell it in the form of, sell it coming from softwood sources, while hardwood is used very rarely. Then, to these samples, we added Herzberg reagent, which is a mixture of zinc chloride, potassium iodide, and iodine, used to qualitative assess the content of lignin in the samples. In fact, the samples turn green if we talk about mechanical pulp, yellow for semi-chemical pulp, and purple in chemical pulp. Then, we choose two of this material having the same chain length. They belong to softwood family, but they had different content of lignin. And these samples were molded in the shape of cellulose caps with the same molding parameters. Then we assess a top load test in which the results are pretty clear. The caps with more lignin behave better than the one with less lignin, having a top load more than the double of the first one. So lignin can be a useful tool to mold some cellulose cap. So you know very well that cellulose isn't a very good water barrier agent. So we added some additives, two different types. The first one is a bio-based mixture that doesn't bind covalently to cellulose, added by spray coating before the molding. And the second one, it's the alkyl ketene dimer, AKD, a sizing agent that forms a covalent bond with cellulose, and it's well known in literature that enhances hydrophobicity. Even in this case, the additives was added by spray coating before the molding. Both of the coating were give hydrophobicity. In fact, as we can see on the graph on the left, the water contact angle in the first 2 minutes were very good, between 110 and 130 degrees. But if we submerge the samples in water for 1 hour, the two different additives behave very differently. In fact, the AKD absorb only the 25% of water in weight, while the other solution, the bio-based one, behave worse than the cellulose itself. And this trend is confirmed when we assess tensile tests with a dynamometer. And in fact, even the dry samples of the cellulose coated with bio-based solution behave poorly, having a low Young modulus and a low tensile strength, while cellulose plus AKD behave well both in the dry and in wet condition, lowering its Young modulus only 5 times against the 20 times of cellulose plus bio-based solution. In conclusion, we can say that optical characterization is the first step we have to make to reject some sample with non-proper features, but we have to implement chemical characterization, such as the pH of the fibers, the titration of lignin to quantitative determinate, and many more. Mechanical characterization instead give information about the molding process, about the specific we have to maintain, and even in this case we have to improve it, obtaining more samples and switching the condition. Having in mind that additives can modify correlation between raw cellulose and molded objects. Thank you.
Okay, thanks Nicolò for the nice talk. And do we have any question from the audience? Okay, so we have a question there.
Okay, thank you for the nice presentation. I have just a curiosity. I wanted to know if you ever considered to use for these products bacterial cellulose or derived from bacteria. And since maybe it's more pure, I saw that the lignin could be helpful, but maybe the color, as I saw, it's brown, so maybe it is not suitable for all applications.
Do you mean as an additive or in bulk? Okay. Maybe it's better as an additive. We haven't tried yet, but since the mole of the objects they thing to make, it's very large. I don't think that bacterial cellulose is suitable for this kind of application.
Okay, so we have another question.
I have just one question out of curiosity. When you used lignin, did you find any difference when working with organosolv or craft lignin, and there is any influence from the source of the lignin itself on the results?
When I speak about lignin in here, okay, this is not added lignin. It's come itself from the cellulose paste, from the wood, as I can say. So I can't recall any difference. And what was the second question? Sorry.
If it was about if there was any influence on the mechanical properties, on the final mechanical properties, coming from the source of the material itself. Okay, the plant source.
Okay, producers tend to not mention the source. So this is the only characterization I can make at this moment. So I can tell if it's pine or some other wood, where it comes from, the age. So it would be better to know it, but at the moment I can't. Thank you.
That's perfect. Thank you.
Okay, so we can thank again Nicolò. And we welcome our next speaker, who is Arianna Chiappa, with application of fused deposition mode lignin in the customization of pharmaceutical dosage forms containing timapiprant. Thanks. So, okay, you can go.
morning, everyone. I'm a PhD student in materials engineering at the Politecnico di Milano. Today, I would like to present a part of my master degree work, which was born from a collaboration between Chiesi Farmaceutici SPA and University of Milan. The project involved the 3D printing of personalized personalized pharmaceutical dosage forms containing timapipran. 3D printing by fused position modeling is an extrusion-based additive process in which the starting material containing the drug is melted or softened by passing through heated chamber, and then it is layered by a nozzle in XYZ direction to build up the final object, following a digital design. In pharmaceutical field, the advantages are the ability to produce small batches of personalized medicine with low cost of equipment. The final object can be personalized by changing directly size, geometry, and process parameters by software, or by customized the feeding materials by hot melt extrusion process. The possibility of interventing to these steps allows to obtain a final medicine with a personalized drug release profile. Chiesi is interested in exploring this technique and provide us an active molecule named timapipran, and asked us to realize personalized dosage forms with conventional dissolution performance, which means that the 80% of the active ingredient has to be dissolved within 30 minutes. Looking at the figure report as an example, only the curve A satisfies this requirement. About timapipran, it is a low soluble molecule, and it is an ion melting compound. For the experimental work, a screening phase was conducted, and we considered some pharmaceutical grade polymers that are, first of all, thermoplastic and hydrophilic in nature. Some of them are promptly soluble, and others are swellable with low molecular weight, and others are used in forming solid amorphous dispersions. For what concerns the extrusion trials, the type and amount of plasticizer and the process parameters was chosen based on literature data and previous trial and error experiments. The increasing in amount of timapipran, ranging from 5 to 30%, was considered, and it was possible to obtain filament for all the formulations. For what concerns the FDM trials, again, the temperature was chosen by trial and error approach. For these trials, was chosen a simple geometry that consists in a cylinder with dimension reported in figure, and the geometry were printed with different percentage of infill to investigate how this parameter impact on the solution performance. FDM trials was more discriminatory in respect of the extrusion trials. In fact, some formulation failed with the test, and they are reported in gray. Only for free formulation, it will be possible produce a sample with increasing amount of timapipran, and it is important to be considered if you want to obtain personalized final medicine with a small dimension. Among these three formulations, the Soluplast-based one has to be discharged because the samples tend to form matrix, and so doesn't satisfy the dissolution requirement. The Kira-based formulation instead got worse, increasing the amount of timapipran, and also this formulation was discharged. PVA-based formulation was the best compromise between the processability by FDM, the dissolution performance, and the versatility of timapipran content. The works went on focusing on this most promising formulation, and it's investigated the impact of the value of surface area on the dissolution performance, comparing the printed prototypes with some references such as the extruded filament, a milled filament, and then the timapiplant powder as such. The results show that the value of surface area impact on the dissolution performance, and as we can see in the figure, and also the formulation impact the dissolution of the active molecule. It was interesting that the printed sample behaves also like the powder reference. So it is an interesting result. At the end of the project, we focus on the design of a final product realized with PVA-based formulation, and that had to be convey 50 milligrams of timapiplant. The final geometry that we chose were cylinder, smaller than the previous one, as vivo, a hexagon, simplex hexagon, and hexagon with Casey's logo, a drop, and a spiral drop. The dissolution performance are quite good for almost samples. And so the results obtained were satisfactory. The feasibility of producing dosage forms containing timapiplant personalized in terms of shape, composition, and performance by FTM was demonstrated. But, however, this work was based on a trial and error approach that is expensive and time-consuming. So in my PhD program, I would like to change this approach with a more rational method in which structure properties and processing, in which the correlation between structure properties and processing and performance of final drug delivery system are investigated. Thank you for the attention.
Okay, thanks Arianna for the interesting talk. And now we have time for questions from the audience. Is there any? If not, okay, so we've got one.
Hello, thank you for your presentation. My question is, a patient, how would assume the drug in with your device? It is like you apply on the skin,
no.
It is to be ingested, I don't know.
These pharmaceutical dosage forms is a thing about the oral administration.
Okay.
So like a tablet.
Okay, thank you.
Okay, so I have a curiosity for you. I was wondering, what would be the advantage of 3D printing in this particular, like, why not just extruding the pill into a mold?
The tablet that the company tried to produce containing surfactant to improve the solubility of this active molecule that has low solubility. By the extrusion process and FDM process, we can improve the solubility of this sample. And we can also improve the value of surface area, so aqueous fluids can solubilize better the active molecule.
Okay, thank you. And if there are no more questions, I would thank again Arianna. And now it's time for the next presentation from Fulvia Cravero, which is about the correlation between morphology and processing parameters in polymer blends, preliminary results towards hierarchical structures.
Okay. So Fulvia, when you wish.
Thank you for the presentation and good morning everyone. Today I'm going to describe you the preliminary results of my PhD study that aims to obtain hierarchical structure through processing. First of all, what is a hierarchical structure? And to explain so, I borrow some example from nature. As you can see here, we have an example of a tendon. And this structure of the tendon is characterized by different organization of the structure at different length scale. This is exactly what is meant as a hierarchical structure. Of course, as you can imagine, this kind of structure is already known, and we have also seen some example in these days and in other presentations. However, these approaches are characterized by some limitations. So first of all, these are usually batches productions, and moreover are characterized by the use of solvents, which can be an issue by considering, for example, environmental impact. So this is where my project starts, and this is the idea behind the project. So I would like to obtain this kind of structure with processing. Also, this topic is already known in literature, and in particular is exploited for the obtainance of shish kebab microstructure in HDPE blends. And from the literature, I obtained some important information. So first of all, I know that if I want this kind of structure, I need a bimodal matrix, bimodal in terms of molecular weight, and in this matrix I need to have also ultra-high molecular weight polyethylene. Moreover, this kind of structure so far have been obtained with compounding or injection molding, and in some cases an external stress was used. However, in literature there are some lacks. So first of all, the matrix is so far often obtained with ad hoc synthesized matrix. Moreover, there is a lack of modelization that links somehow the parameters with the final morphology. So this is the starting point of my first year of PhD. On one hand, I want to obtain a model that links the parameters with the microstructure. On the other hand, I would also like to assess the exploiting of commercial HDPE as a feasible matrix. So I selected two HDPE, a high molecular weight and a low molecular weight HDPE to mimic this kind of bimodal distribution. And then I blended these two materials, and I've characterized it with DSC and rheology. As I mentioned before, I would like to obtain a model. And of course, a model requires to have some parameters of control. My parameters are so far the blend composition, the processing temperature, and the speed rotation screw, where these two last parameters refers to the compounding with a twin screw extruder. By combining all these parameters here, I ended up with 20 compoundings because I wanted to test all the parameters together. So here I just show you briefly some results. First problem was that by just looking at the results of one of the two matrices, and of course it's the same for the other, as you can see, there is difference, so there is effect of the parameters, temperature and speed rotation screw, just considering one matrix. So I had to find out how to homogenize and to have a point to compare everything together. So I decided to use the fusion, the melting enthalpy of the pellet of the as-received materials as a starting point, and I referred this value to all the other enthalpy I measured. So here you can see for the comparison for the composition. So here we have 70, 50, and 30% of one matrix in the other. And as you can see, there is an effect of the combined RPM and temperature on the gap of the enthalpy. So if I want to obtain a larger gap, I need, in all cases, to have low RPM and higher temperature. However, if I want to obtain a smaller gap, I can appreciate that also the composition of the blend is important. Then I also tested my blends with the rheology. And here is just, as you can see there, one RPM, one parameter of RPM and one parameter of temperature. So here in all the graphs, you see the fitting models for depending on the blend. I've tested 3 different fitting models: a linear, a diluted emulsion, and a logarithmic fitting. And these, of course, are the comparison. From the rheology, we can also obtain some interesting points. So first of all, as you can see, the different molecular weight affects both the Newtonian behavior and the zero shear viscosity. These make me thought that my blend may not be completely miscible. However, just looking at the fitting comparison, you can see that the better one that fits my data is the logarithmic fitting. So I so far could conclude that these two matrices are completely miscible. So from this preliminary study, I ended up with some conclusion. Firstly, I could appreciate that the enthalpy and the torque can be related to the processing condition, and also that my viscosity, the viscosity of my blends, can be also related to the composition through a logarithmic fitting. As I mentioned before, I'm in my first year. These are just preliminary results, so I have a lot of plan on what to do in the next steps. First of all, referring to the data investigation, so the data that I have so far, I would like to apply PCA analysis on my rheology data to extract more information. Then I would also like to apply an ANOVA method on my DSC results because, as you can appreciate, I have a 2-3 model. Then I would also like to try to extract information from XRD analysis. And lastly, to understand better the shear inside my extruder with simulation with Ludovic. Then, when this kind of, with this information will be assessed, I will then further input other parameters in my system, so by adding ultra-high molecular weight polyethylene and to apply also an elongational stress. So I would like to thank my colleagues and the committee organization, and of course you for your attention. Thank you.
Okay, thanks Fulvia for the nice presentation. Now we have time for some questions from the audience. Okay, as everyone is shy, I'm going to ask a question. So I missed, maybe you said it, but like for which purpose, which kind of application do you think that these materials will be suited once you have optimized your parameters?
Thank you for the question. No, I didn't mention that because actually there are already some examples in literature, especially depending on the composition of the blend. So some application refers to more functional or structural application, while others, for example, with conducting fillers, may refer to the application in electrical fields or conductive coatings or things like that. But so far, due to the fact that I found this kind of lack of information and modelization, I haven't talked to a proper application while I just want to understand how to work in the background, and then I will decide how to exploit it in the next steps.
Okay, thanks. So if we do not have any other questions, I think we can thank again Fulvia. And we can welcome our next speaker, who is Federica Daus,
with characterization of bacterial cellulose from kombucha tea. Okay, so the stage is yours.
Thank you. Okay, so good morning, everyone. Today I will talk about the characterization of bacterial cellulose from kombucha tea. So, as is already been said before, cellulose is one of the most abundant biopolymers on Earth. It is made of beta-1,4-linked glucose units called cellobiose, and it is a biocompatible and non-toxic polymer, which is normally extracted from plants, but it can also be produced by few bacterial strains. And in this case, it goes under the name of bacterial cellulose, which is secreted in form of ribbons composed of microfibrils and protofibers. And each protofiber contains nanometric parallel chains, and the three-dimensional network of hydrogen bonds results in a highly compact crystalline structure with a higher index of crystallinity compared to plant cellulose. So the material shows a high hydrophilicity, a great water holding capacity, and a high surface area due to its nanometric dimensions. Moreover, it doesn't contain any hemicellulose or lignin, so it doesn't require any harsh chemical treatments to be purified like plant cellulose does. So all these properties make bacterial cellulose a suitable alternative green material that can be used for a wide range of applications, going from cosmetics to packaging, fashion industry, and biomedical field. So bacterial cellulose can be obtained from many different media, but in my project I'm focusing on the one obtained as a byproduct of kombucha tea fermentation. So kombucha tea is a slightly alcoholic beverage obtained from the fermentation of tea leaves and sugar. And during this fermentation, a symbiotic culture of bacteria and yeasts is obtained, called SCOBY. And from the purification of SCOBY, bacterial cellulose is obtained. So what happens within this ecosystem is the accumulation of ethanol and acetic acid, which forms a film at the air-liquid interface. And the film thickens as the fermentation continues, until the oxygen supplement is sufficient. When there is no more oxygen available, then the fermentation stops, the process stops, and the bacteria remain in a quiescent status. So a first characterization of SCOBY and bacterial cellulose was performed. From the X-ray diffraction analysis, we can see that both of the two materials have a cellulose-1 kind of crystalline structure. So from here we can see that the purification protocol doesn't affect the crystalline structure of the biopolymer. From the ATR analysis, we can see that they have a similar spectrum besides from the bands related to the hydroxyl groups, which are less intense in the purified sample because of the purification process. And from the thermogravimetric analysis, we can see that they have a different thermal degradation profile. So the SCOBY degrades into steps and the cellulose in one only. And the residue at 600 Celsius degrees is lower, of course, in the purified sample because of the removal of bacteria and all the impurities. And then the morphology of the samples was studied by means of the scanning electron microscopy. So here we can see that the surface of the SCOBY presents yeasts, bacteria, and salts, while the bacterial cellulose one looks smoother and cleaner. And if we go even closer, we can see the fibrils on the surface. Both of them show a multi-layer structure, which is due to the purification, to the fermentation process. And again, here we can see the nanometric fibers that characterize the cellulose structure. Then the mechanical properties were analyzed, and both of them, after the drying process, look very brittle and fragile, and they break very easily when stretched. And this is also confirmed from the elastic moduli of both of them, which are very high, and they increase, and the elastic modulus increases after the purification process. So in order to improve the mechanical properties of cellulose, a plastifying agent was used, in particular glycerol, which not only covers cellulose surface, but it also penetrates into the structure, forming hydrogen bonds with hydroxyl groups. so increasing the space between the fibers and facilitating their movement. So this results in a material that can be easily deformed without breaking. Then the analysis were repeated on the treated samples, and again here we can see that the crystalline structure is maintained after the treatment. From the ATR analysis, we see that glycerol is present in the composite as the bands related to the hydroxyl groups and the carbonyl groups are greatly enhanced. And from the thermogravimetric analysis, we can see that the composite has a different thermal degradation profile. Of course, this is due to the presence of glycerol and bacterial cellulose. And finally, and then from here we can see that the cellulose and glycerol are in a ratio of 1:3 in the composite. Finally, mechanical properties were analyzed again, and as expected, we can see that the material doesn't break anymore, so it can be deformed more easily, and this is confirmed from the elastic modulus, which decreased, and the elongation of break increased. So in conclusion, we can say that bacterial cellulose is a green alternative material that can be used for a wide range of applications thanks to its outstanding properties. And it can be obtained from different media, including kombucha tea and especially its byproduct, the SCOBY. And even if the dried material looks brittle and fragile, its mechanical properties can be improved by the addition of a plastifying agent like glycerol. So finally, I want to thank my supervisor and the company I'm working with for getting me through this project, and of course the European Union for financing it. And thank you all for your kind attention.
Okay, thanks Federica for the interesting talk. Do we have any question from the audience? Yeah.
Thank you for your nice presentation. I have two questions, if I may. The first one is, did you come to a quantitative evaluation of the crystallinity through XRD? And the second, sorry, yes, just to pass the mic. The second is, how did you add glycerol? So you started from the dry film, the wet film, how? Thank you.
Okay, thank you. Regarding the crystallinity index, I didn't calculate it because from the diffractogram, as you can see, it is very difficult to, let's say, differentiate the curve related to the amorphous part and the crystalline part. But the main purpose of that kind of analysis was to see if the purification process affected somehow the crystallinity of the sample. And it didn't, because the width at the half of the height is basically the same. And for what regards the glycerol treatment, I used a dried film, and I just poured a few drops of glycerol, of pure glycerol, on the film, and with our hands, I tried to facilitate the penetration of glycerol inside the structure. So just with mechanical, let's say, method. Thank you.
Okay, so if there are no more questions, I will thank again Federica. And now for our next speaker, we have Luana Di Lisa with the development of a novel 3D bioprintable hydrogel formulation based on decellularized extracellular matrix and gelatin methacrylate.
Okay. Good morning, everyone. I present my work, which is based on the development of a novel 3D bioprintable hydrogel formulation based on the cellularized extracellular matrix and gelatin methacrylate. So, a brief introduction to what is 3D bioprinting. It is a powerful technology which allows the use of bioinks for the manufactures of two-dimensional structures capable of representing the complex environment in which cells naturally live. And it has many applications such as tissue engineering and regenerative medicine. My work in this field, in the extrusion bioprinting, is focused on the development of bioink, which are composed mainly of cells and biomaterials. And then it is put into a syringe and extruded through a nozzle in order to obtain a two-dimensional biological model.
In order to obtain this goal, it is important to follow a strict workflow in which the first step regards the hydrogel preparation and characterization, of course the rheological assessment. Then it is important to select the right cell source in order to obtain the final bioink formulation. Again, the rheological evaluation to correlate the rheological properties with the printability of the bioink final formulation, which is then used for the fabrication of a 3D bioprinted model. And of course, the evaluation of the model is conducted with biological characterization. So, the printability assessment in extrusion bioprinting process is a key point. We can consider the entire process divided into 3 different steps, in which the first one, the hydrogel is in the syringe in static condition and it must support cells. So we can study the viscoelastic properties of the materials with an amplitude sweep test in which we should see a gel-like behavior, so an elastic modulus higher than the loss modulus. Then, during the extrusion, the material should be printable, and we can assess this behavior through the flow curve test, in which we should see a shear thinning behavior, so the viscosity decrease as a function of the shear rate. Then, after the extrusion, the material should recover its mechanical properties, and we can assess it through the 3ETT test. So, as regards my work, I focus firstly on the hydrogel preparation. How we can select the right biomaterials. We have to think about that we have to mimic as much as possible the extracellular matrix, which is composed of macromolecular components which are strictly connected to the function of the target tissue that we want to recreate. So among the many biomaterials such as collagen, alginate, hyaluronic acid, I choose to focus my work on an hydrogel based on the cellularized extracellular matrix because it preserves the complex environment of the native ECM, even if it has low mechanical properties. So we obtained from the tissue graft component a DECM hydrogels from bovine pericardium, and we firstly assess the rheological properties of these materials. For time reason, I will not show the complete rheological evaluation, but for example, from this time sweep test, we placed the material 37 degrees for 1 hour, and we saw that after 30 minutes, the elastic modulus and the loss modulus increase, thanks to the thermal cross-linking of collagen, which is the main component of the DECM. But it is a weak cross-linking, so we need to improve the mechanical properties for the 3D bioprinting application. And so we think to mix it and cross-link it in the presence of the second biomaterial in order to obtain an interpenetrating polymeric network system. And so we think to mix it with gelatin methacrylate thanks to its biocompatibility and for the possibility to tune the mechanical properties by modifying the parameters of the photopolymerization. And so we synthesize the gelatin methacrylate through a methacrylic reaction on the hydroxyl and amino group present on the lateral chains of gelatin. So we obtained this formulation of the EPN based on DECM and GELMA by firstly mix them in a 50-50 ratio, so obtaining the blend. Then we put it at 37 degrees for 1 hour for the thermal cross-linking of the DECM, and then we obtaining the semi-EPN in which we added the photoinitiator, the IrgaCure, and then after the extrusion process we cross-link the material for different time of UV exposure in order to optimize the EPN formulation. And so we study the rheological properties of the different EPN formulations, and what we can see is that all the material shows a gel-like behavior, but of course by increasing the UV time exposure, the elastic modulus increased. And we were able to select an EPN formulation cross-linked for 2 minutes because they were enough to reach the target value of storage modulus.
Then we simulate the entire extrusion process with this test, the 3ETT. And so we firstly apply to the material a low shear rate by simulating the pre-extrusion phase, and we study the viscosity of the system. Then we study the viscosity of the same EPN formulation during the extrusion by applying to it a high shear rate and by considering the real dimension of the nozzle and of the syringe that was used for the printing process. And then we study the capability of the system to recover the initial viscosity by applying to it again a low shear rate. And what we can see is that our material is able to recover the mechanical properties after the extrusion. As regards the morphological analysis, we saw that the DECM cross-linked shows flat structures, while the EPN cross-linked shows a cross-linked structure, which is useful for the cell's encapsulation, and it shows a homogeneous distribution of the pore size. And finally, as regards the fabrication of a 3D bioprinted model, we firstly optimize the printing parameters for the bioprinter Regemat W1, like the nozzle diameters, the flow speed, the geometry of the scaffold, the temperature of printing, and we obtain the 3D bioprinted scaffold with high shape fidelity. And then we focus on a bioengineered skeletal muscle, because our aim is to compare from a biological point of view our new formulation in which we will embed the myoblast from patients and the photoinitiator with an already assessed bioink that is based on collagen and myoblast from patients in order to obtain these like aligned myofiber structures, in both cases cross-linked with UV for 2 minutes. And for example, these are very preliminary biological studies that were conducted on the collagen bioink, in which we simply saw that the myoblasts were good in the matrix since they have an elongated shape. So, in conclusion, we optimized the EPN based on the DECM and GELMA. We studied the rheological properties of their system, and we assessed that EPN presents better tunable stiffness and better biological properties. We selected the right cell source for the target tissues that we want to recreate. We optimized the printing parameters in order to obtain constructs with high shape fidelity, and as regards the biological characterization will be performed in the near future. So I would like to thank my group, the Polymer Science and Biomaterials groups of the University of Bologna, and you for the attention.
Okay, thanks Luana for the nice presentation, and we have time for some questions from the audience. If no one is going to ask anything, I was wondering about the technical limitations of the process, like how big of a sample you can make and how small of a line you can draw with the 3D printing, with this kind of 3D printing.
Okay, we usually use multi-well for the biological assays, so we need constructs like 10 millimeters of diameters for this type of biological studies.
Okay, thank you. And if there are no more questions, we can thank again Luana. And we can welcome the next speaker, who is Dario Fontana, with conducting polymers as anti-corrosion coatings.
Good morning, and thank you for the opportunity of presenting me and my PhD project about conducting polymers as anti-corrosive coatings. Normally, people is not actually aware of how important is corrosion prevention in everyday life. In fact, it is important from an economical point of view. In fact, according to the National Association of Corrosion Experts in USA, it costs around the 3 and 5% of the world GDP. It's important also because of environmental concerns, also to protect our cultural heritage, but most of all, in order to protect human life. But before, let me introduce myself. I started studying chemistry at the University of Milan, where I got both my bachelor and master degree. During my master degree, I spent 7 months in Sorbonne University, and for my final thesis work, I worked with a National Council of Research with a project about biopolyurethanes. Now I am a PhD student of the first year at the University of Pavia with this project to tackle all the problem of corrosion prevention in collaboration with ANI and University of Santa Barbara in California. This is the reason why today I cannot show you all my results because of intellectual property reasons. Talking about corrosion, generally speaking, it's an electrochemical process involving metal surfaces where there are two contemporary reactions: the oxidation of the metal, in this case iron, and the reduction of oxygen with the formation of rust. And this causes the fragilization of metal and also its partial solubilization. In order to tackle this challenge, I chose conductive polymers because and particularly PDET, polyethylene dioxythiophene, and PANI polyaniline, because as you can see, they are constituted by a highly conjugated system of long polymers, where if they are doped, we can have a delocalization of electrons and charges, providing them not only conduction but also electrochemical and redox properties that can interfere with the electrochemical process of corrosion. And for this reason, they could be a very high performance class of material. First of all, PDET. PDET it can have a very good conductivity if doped with polystyrene sulfonate, for example. It has an excellent thermal stability, and it's an insoluble polymer. This latest characteristics is often seen as a disadvantage, but in our case, it can be a very good advantage in order not to be solubilized in water. Although there's not so much literature about PDET used as anti-corrosive agent or coating, there is a huge quantity of synthetic information about this polymer, so we can tune its properties by organic functionalization, by tuning electron richness, the steric strain band gap, and more specifically for our purposes, also the self-doping, hydrophobicity of the polymer, or also providing reactive groups that can give cross-linking. While polyaniline is most well known in the field of anti-corrosion, and it's very particular because this polymer can acquire different forms according to its level of oxidation and doping. Leucoimiraldine is the most reduced form, pernogranulin the most oxidized one. They are both non-conductive, while imiraldine base is a partially oxidized form, and emeraldine salt is the doped one. Thanks to this characteristic, polyaniline can naturally provide corrosion protection by modulating the corrosion on the metal surface and forming and maintaining a passive layer, naturally protecting the metal beneath. So it's an anodic protection. But even if polyaniline has such interesting and advantageous inherent anti-corrosion behavior, it is necessary to isolate the metal surface from the corrosive agents, so from water, by tuning the morphology of our coating, or the organic functionalization. I obtained a PDET-based polymer presenting as a purple powder with brown shades that can be dissolved and solubilized actually in chloroform, THF, and toluene. And I also deposited it in films from chloroform and toluene solutions using spin coating technique and drop casting, trying to optimize the process. And I obtained also some encouraging results about the static contact angle on glass by using solutions of this polymer. And I observed quite a hydrophobic behavior, especially for solutions of concentrations measured to 10 milligrams over milliliters. So in conclusion, I can say that in this first year I obtained a PDET-based coating whose also polymerization conditions were screened. It is hydrophobic, and I've been able to film it. So the first goal now is to characterize its performance against corrosion. Thank you for your attention. I'm open for contacts. We are open for collaborations, so please contact me if you're interested in my project or even chat. Thank you.
Okay, thank you, Dario, for the nice presentation. And do we have some questions? Yes, we got them. Maybe Eduardo is close enough.
Hello, thank you for your presentation. I have just one curiosity about the next perspectives of your work, if you can tell me. Which will be the test, how will be the test, the anti-corrosive, like the operative conditions in which you will test the materials?
Okay, thank you for your question. I written operative tests, but before the actual operative tests, we need a basic electrochemical characterization, which is at least cyclic voltammetry, differential pulse voltammetry, of course, open circuit potential, in order to have already an idea of the anti-corrosive property of the material. Then, also electrochemical impedance spectroscopy is a key characterization, because it can give us a lot of useful parameters about how the protective layer is electrochemically characterized over just protection. It allows us to rationalize the process, also to change parameters if it's not good. And we can also obtain water absorption information from this technique. After that, we will have operative condition in atmospheric, so air, or in water, salt water. And if it's good, we can try and we can expose it to, I don't know, sulfuric acid, highly, or even bacterial corrosion. But this is very far.
All right, thank you very much.
Thank you for your nice presentation, very interesting. I don't know if you can tell something about your preliminary results on conductivity of your polymer.
Okay. What I can tell you is that if you want conductivity, it is necessary to dope this kind of polymers. So if you don't dope them, they are just they have normally semi-metallic behavior. In order to provide corrosion protection, there's no strict law. It's not mandatory to have a highly conductive polymer, because actually this could provide an enhance of corrosion. It depends. It depends on what is your polymer, if it's a PDET, polyaniline, or other conductive polymers, what is the formulation if you have additives in it and functionalization. So I spoke about anodic protection, but you can provide protection also by adding inhibitors in your polymer, or even by providing a coating system which is formed by layers of different conducting polymers.
Thank you.
You're welcome.
Thanks for the presentation. Curiosity, because my knowledge about coatings is very scarce. But what are the advantages in using a conductive polymer for the coating respect the classic ones?
Yeah, classic strategies are constituted by adding corrosion inhibitors inside the metal formulation of the alloy. So we are not speaking about coatings. They're very efficient, but they are also highly toxic normally. So nowadays they normally or thicken the iron, for example, layer of the mechanical piece, or you protect it by thermosets, polymers, polyurethane, epoxies. But the problem related with these kind of polymers, as many of you have said, is that they are petroleum derived, or they are very difficult to recycle. With conducting polymers, we are trying to get materials, coatings, with a high performances that can sum the barrier effect, so hydrophobicity, cross-linking, but also exploiting their electrochemical properties that we hope could enhance the duration of their action. So even if maybe they could be a bit more expensive than an epoxy, they would last more. So it would be good for industry.
Okay, thanks.
Okay, so thank again, Dario.
Thank you.
And now it's the turn of Mattia Fornaro with the effect of cross-linking density on the properties of reprocessable Diels-Alder epoxy-based thermosets. The stage is yours.
Okay, good morning everybody. I'm Mattia Fornaro, and PhD student since January at the University of Naples Federico II in Industrial Product and Process Engineering. Today I am presenting you my degree thesis concerning reprocessable epoxy-based thermosets. Why was this topic chosen? If we consider conventional epoxy-based thermosets, we're going to say that these materials are very useful nowadays to their very important technological properties and versatility. However, we're also going to say that these materials cannot be recycled after the curing reaction. That leads to strong irreversible covalent bonds. And therefore, this is surely a sustainability issue if you consider that this material has a growing demand in the market year by year. The strategy that we opted for was the Diels-Alder reaction. What is Diels-Alder reaction? It is a cycloaddition reaction that involves a diene, in our case a furan ring, and a dienophile, in our case a malamide. We can imagine of modifying a conventional resin with dependent furans. We will call this a furfurated resin, and curing it with a malamide hardener, obtaining a Diels-Alder thermoset. The advantage of this reaction it is thermo-reversible, allowing the wastes of these materials to be recycled and reprocessed at temperatures that are higher than the ones of the curing reaction. The raw materials that were used were GEBA, the conventional epoxy precursor, then furfuryl alcohol and furfuryl amine that provided dependent furans to the conventional GEBA. Two new precursors were then synthesized, in particular by direction of GEBA and furfuryl alcohol. The furfurylated epoxy resin from alcohol was obtained, we can see the monomeric structure of this precursor, and also the sulfurated epoxy resin obtained by amine. And here we can see the polymeric structure of this precursor. Then bismaleimide was our hardener that provided, of course, the links as a bridge between two pendant furans. So we need one bismaleimide for each two pendant furans. Then we prepared blended formulations of precursors by varying the sulfurated epoxy resin of aminic and alcoholic content. So we can see 100% aminic precursor till a 25% aminic precursor. 4 different blended precursors, which also have an impact of the final cross-linking density. Indeed, comparing to a 100% aminic precursor, increasing the alcoholic content indeed reduces the final cross-linking density to the reduced functionalization due to the sulfuryl alcohol. The performances of these materials were studied as adhesives. So a lab shear test on an aluminum tape that was glued with these different formulations was studied, and we can see that the force, the adhesive force for these 4 formulations were almost similar. However, a trend was observed that increasing the aminic content and therefore the cross-linking density led to a higher adhesive force. Then the flexural performances of these thermosets were also studied. We saw that a higher aminic content and therefore, as I repeat, a higher cross-linking density led to stiffer resins, but with also a higher flexural strength, but also a reduced fracture strain. So surely we can modulate the properties of these materials by varying the aminic over alcoholic contents. Then we studied the properties for the reprocessed samples. And here is shown the procedure that it was executed to reprocess these materials. So we reprocessed them twice, and for each of these reprocessing cycles, we studied the material properties. We saw that no critical embrittlement occurred for these materials, and so they could have a technological use. Of course, there is a reduction between the virgin material, the cycle 0, and the reprocessed ones. Why this happens? Because to reprocess this material, we need high temperatures, around 150 centigrades, to return back to the reagents. However, when these temperatures are reached, the precursor leads to, of course, degradation, and bismaleimide, the hardener, can homopolymerize. And therefore, this adversive phenomena lead to a compressive reduction of the final properties of the reprocessed samples. So, in conclusion, we prepared reprocessable epoxy-based thermosets with different cross-linking densities by varying the aminic over alcoholic content. We saw that the mechanical properties were almost stable between the first and the second cycle of reprocessing. Surely future studies may need to be to study how many times we can reprocess this material, granting a technological use, as we just studied 2 reprocessing cycles. And of course, we also need to optimize the synthesis reactions, as a lot of solvent was required, and of course, this impacts the overall sustainability. But of course, this is surely a very important result in terms of sustainability of the material. I would like to thank you all for your attention, and also the organizers, and the Polyfun, the Polymeric Functional Group, for the support during my thesis. Thank you.
Okay, thank you, Mattia. So do we have any questions from the audience? We do.
Hi, thank you very much for your nice presentation. I noticed there is a very good retention between cycle 1 and cycle 2. So my question is there a cycle 3? Is there you still need to test? And my question is, theoretically, as an idea, how many cycles do you expect to perform to keep the properties? I mean, unities 10 times, 100 times. Brief idea, of course. Thank you.
Thanks for your interesting questions. No, we just studied 2 reprocessing cycles. Well, we tried testing a 3rd cycle, but the embrittlement was increasing very highly. But yeah, we can also optimize the reprocessing itself. How many cycles? In literature, I found also 5, 6 reprocessing cycles. So it surely can be reprocessed more times, but the mechanical properties have to be granted. So I cannot answer properly to your question, but I don't imagine many more cycles. At least with this procedure, maybe optimizing the word synthesis may be useful for the final recycled properties. Thank you.
Thanks for the presentation, and I wanted to ask that if you know if there is some strategy to apply during the reprocessing process for not having the homopolarization and so the embrittlement of the material after the reprocessing, and so if you can apply some strategies to not have this phenomenon.
This is also a very interesting question. The rate of decide direction, it is not one temperature, it's a very broad range of temperatures. Of course, choosing the proper temperature is important also for the final efficiency of the material. To be honest, the homopolymerization of bismaleimide occurs also at low temperatures. The bottom, the rate of decide direction also includes the homopolymerization of BMI. So what we try to do is reducing as much as possible the reprocessing time. Here we just did 5 minutes at high temperatures. So the temperature was high, but the reaction time for those adverse phenomena was very little. So the time combined with a proper temperature is useful to reduce these adversive phenomena.
For example, you have maybe thought to add some kinds of reactant during the reprocessing process, maybe adding some molecules to not have these reaction side reactions. You think that's maybe is possible, maybe not? What's your
It
opinion?
really is a good idea, but yes.
Thank you.
Thank you.
Okay, so thank you again, Mattia. And we can proceed with the next speaker, who is Luigi Gamberini, with a novel method to cross-link electrospan pullulant membranes containing carbon dots for water purification. Okay, so the stage is yours.
Good morning to you all. My name is Luigi Gamberini. I would like to show you my work about a novel method to cross-link electrospun pullulan membranes containing carbon dots for water purification. First of all, what is pullulan? Pullulan is a natural polysaccharide made of a triose of glucose. Among these features, there are biocompatibility, biodegradability, bioadhesivity. It is a non-toxic polymer. It is available on the market, and it is relatively cheap. However, one issue is that it is a water-soluble polymer, and this hampers the use of pullulan as a material for in-water applications. What is the answer to this? It is to cross-link it in order to improve its mechanical and physicochemical properties and also to induce water resistance. In our lab, we studied the fabrication of nanofibrous membranes by electrospinning, which are no-woven mats with high surface over volume ratio. These membranes, if made of pullulan, are not suitable for in-water applications like water filtration. And it is not a viable alternative to synthetic polymers. However, the interesting thing of pullulan is that it can be directly dissolved in water. And water is greener than many organic solvents used for polymeric solution to electrospin. So how we can achieve a cross-link that makes the membrane viable for an in-water application, maintaining the nanostructure, but also to make pullulan still soluble in water. Many strategies have been tried. One is the physical cross-linking of pullulan by plasma treatment, already published by your lab. The second, we studied chemical modification by metacrylation, followed by UV reticulation, but few results have been obtained by that. The one I want to talk about is the chemical cross-linking using tetraethyl orthosilicate, THEOS, as a cross-linking agent. How it works is the reaction. First of all, there is the acidic activation of THEOS, which forms the tetrahydroxysilane, which is capable to react with one chain of the pullulan, sinylating it. To link the chains, another chains must react with the same active species, forming a link between them. The steps for the mat production is, first of all, the dissolution in water of pullulan, followed by the addition of the acid and THEOS, and the homogenization by vigorous stirring. The polymeric solution is then electrospun, and the mat obtained is put in water for thermal curing. The optimized parameters for the reactions are the THEOS over pullulan weight ratio, the thermal treatment, the thermal temperature, and the time for the thermal curing. Why we need the thermal treatment? As you can see, an S-span membrane is still soluble in water because the reaction between the chains and the cross-linker happens in solido. And after a thermal treatment, instead, the membrane is insoluble in water. So we observe that the temperature speeds up the kinetic of the reaction. And how can we evaluated the cross-linking degree of the membrane by gel content measures, which measures the amount of pullulan that remains after the exposure to water. And we observed that optimizing our parameters above stated, we reached the high values of gel content, near 100%, which is needed to in-water application. From the IR spectra of the mat, we observed that the silylation occurs because there is the increasing of the silicon-oxygen stretching bands. And from a thermogravimetric analysis, we observed that cross-linking increased the stability of the polymer in thermo-oxidative condition and also remains silica residual. Until now, we observed that the polymer is now stable in water. But what about the fibers? Well, we observed from that before and after water immersion, the fiber morphology are maintained by the same images. So now we have produced a good membrane for in-water application, and my research of Zorlab was part of an international project called Bio-Based and Biodegradable Carbon Dot Polymeric Nanofibrous Membranes for Solar-Assisted Water Remediation and Oil Spills Cleanup, which aims to create a nanofibrous membrane loaded with carbon dots, which are nanoparticles with photothermal activity, capable of remove water pollutants. So, which I tried to add the carbon dots inside the polymeric solution by mixing it, and we obtained to reach a load up to the 20% weight over weight ratio. We can observe the blank meth and the loaded meth. There's a difference in color, and the same images taken before and after water immersion reveals that the nanofiber morphology is maintained. The conclusion of my work is that we successfully cross-linked the pullulan with Theos, and which is a novel way of cross-linking it, not reported in literature. The nanofibers are promising for water filtration because we need to test it, and we can think also for other application of other water application, like in the biomedical field. I want to thank Professor Focareta and Professor Gualandi. I want to thank also the other researchers we worked in this project, Monica Torselli and Irene Mondadori Monesi, and the Israeli university which provided us with carbon dots. And last but not least, all our lab. Thank you all for the attention.
Okay, thank you, Luigi, for your nice presentation. And we have some quick questions from the audience. Okay.
Okay, thank you for the presentation. I was just wondering if you could tell us what kind of carbon dots do you use, which is the precursor, and if there are important functional group, and second of all, if the functionalization of carbon dots, the fibers with the carbon dots is just mixing, or do you have like covalent bond between the fibers and the carbon dots, as to see how it works? Thank you.
Thank you for your question. Sorry, I omitted to say that the carbon dots we used are derived from biomass because we wanted to ensure the greenness of the overall project. And yes, I mix it, and I decided to use those kind of carbon dots because we did some IR analysis over them, and we revealed that they presented the hydroxyl groups which are necessary to covalent cross-link it with Theos and the pullulan. So we thought that using them could achieve a covalent cross-linking to link the carbon dots with the polymeric chains.
Okay, so thanks again, Luigi. And last but not least for this session, we have Gianluca Gazzola with oxygen tolerance during surface-initiated photo ATRP, tips and tricks for making brushes under environmental conditions. Pesa 1,76 giga.
Sì, ora.
Ah, ma no, ma perché non
no,
è...
No, tutto, no, solo... Mi sa che sta copiando tutto.
Infatti dicevo,
no,
1,77 giga era un po' tanto. Ok, ok.
So, good morning, everyone. Today I'm going to give you some tips on how to improve oxygen tolerance in surface-initiated atom transfer radical polymerization. First of all, what are brushes? Brushes are polymer assemblies that enable the modification of surfaces to generate new technologically relevant materials, which can find application in several areas. For instance, polymer brushes can be used to reduce the friction between two surfaces or to prevent the adhesion of proteins on them. Moreover, polymer brushes can be also employed to stabilize colloidal dispersion by choosing the right solvent. And they also can find application in the fabrication of smart devices, such as biosensors. Polymer brushes can be synthesized by surface-initiated control radical polymerization. In particular, surface-initiated atom transfer radical polymerization is the most widely applied method, in which control is provided by the reversible activation of an alkyl halide, and this enables the synthesis of polymers with very narrow molecular distribution and high molecular weight. However, there are some limitations. Larger action volumes are required, and this technique is limited to small areas, and it's very sensitive to oxygen. So the translation of surface-initiated atom transfer radical polymerization into technology require the improvement in oxygen tolerance and the development of small reaction volumes and a method that can use a limited amount of catalyst. To overcome these challenges, a very simple setup was used, where a drop of the polymerization mixture is poured on an initiator functionalized substrate, and then a confining gas slide is placed on top of it. After UV light irradiation, the oxidized form of the catalyst, the so-called deactivator, is reduced to the reduced form of the catalyst, the activator, and these species can react with oxygen and consume it by the formation of a superoxide metal complex, which can be reduced back again to the activator. Based on this catalytic system, polymer chains start to grow directly from the surface of the substrate, and the presence of oxygen can inhibit this polymer growth. So the advantage of this setup is the creation of a highly confined small reaction volume, in which the diffusion of oxygen is hampered, and so prior degassing step of the system is not needed. Unfortunately, the diffusion of oxygen is not completely avoided, especially at the edges of this setup, where inhibition of the polymer growth is observed. This phenomenon is called edge effect, and it can be correlated to the oxygen tolerance of the system. So, the objective of this work is to optimize the tolerance of surface-initiated photo ATRP toward environmental conditions, by systematically assessing the role of each parameter of the polymerization. We started with the changing in catalyst concentration, and then we move forward by studying the effect of the addition of a free initiator into the polymerization solution. And in the end, we also investigated the effect of the confinement of this reaction volume by changing the distance between the substrate and the confining gas slide. So, as we can see in these pictures, brushes with different thicknesses and edge effect can be obtained by changing the concentration of catalyst from 0.01 to 10 millimolar, while keeping a polymerization time of 1 hour. Dry thicknesses were recorded with increasing the concentration of the catalyst, showing a maximum around 1 millimolar. The decrease in polymerization rate at higher concentration of the catalyst is probably due to the accumulation of the copper tube-based deactivator. Simultaneously, the decrease in the size of this edge effect with increasing the catalyst concentration indicates faster consumption of oxygen by the catalyst. Following, we decided to study how the presence of a free initiator, in this case ethyl alpha bromoisobutyrate, into the polymerization solution can affect oxygen consumption, and so oxygen tolerance, in the presence of two different catalyst concentrations, 5 millimolars and 0.5 millimolars. Radicals generated in solution from the reaction of this free initiator with copper 1 perform a very effective oxygen trapping. But this process also leads to the accumulation of copper tube-based deactivator. And this is confirmed by the progressive decrease in the polymerization rate with increasing concentration of the free initiator. While the size of the edge effect decreases as the catalyst concentration increases, and thus indicating a very effective oxygen consumption. Finally, we decided to study the effect of the confinement of this reaction volume by changing the distance between the initiator functionalized substrate and the confining dust slide from a quasi-contact situation, more or less 50 micrometers, to almost 0.2 millimeters. Diffusion of oxygen is facilitated by the increasing of the reaction volume. And so a decrease in the dry thickness and increase in the size of the edge effect were observed. So the question is how to gain back oxygen tolerance while keeping the same reaction volume, and so in the absence of the confinement, by the simple addition of a free initiator inside the solution, as the radicals generated in solution combine with oxygen faster than any other component of the solution. And so brushes with a higher dry thickness and with a lower size of this edge effect can be obtained. In conclusion, increasing the concentration of the catalyst, oxygen tolerance increases, but at the expense of polymerization rate. So this indicates that a carefully adjust of the catalyst concentration is needed. Radicals generated in solution from the free initiator act as oxygen scavengers. And in the absence of the confinement, oxygen can freely diffuse into the polymerization mixture, hampering polymer growth. But the presence of a sacrificial initiator provides oxygen tolerance, even when polymer brushes are fabricated into less confined setup. I would like to thank all my colleagues, all the collaborators, and you for your kind attention.
Okay, thank you Gianluca for your interesting presentation, and we have time for just a last quick question to Gianluca. Anyone? Okay, so a quick question. I am wondering, the goal of your research is to kind of make easier further research on brushes by making other people able to work under environmental conditions.
Yeah, it's a mechanistic study. So it reveals some features of this type of process. And so we want to, also because this type of process is limited, since not all the substrate can be functionalized. And so it's quite, it's not so good to waste, for example, silicon in this case. So yeah, it's to improve this technique, to improve this process, and let understand what's happening.
Okay. Okay, so Thanks again, Gianluca, and thank again to all the speakers and the audience for their attention. And now it's lunchtime. Oh, and someone left this USB key? Okay.
Possiamo fare anche subito.
A parte la presentazione, sì, sì, lo penso solo, quello non devo pensare a devo prendere con me una chiavetta. Conoscendomi potrei lasciarla anche su, se vengo il classico. Cado per le scale, sai? Sì, Aspettiamo qualche minutino che entrano tutti.
Okay, so I think we can start. Welcome back from the lunch break. I hope you enjoyed it. So I have the pleasure to present Andrea Giovannelli with his work about solid-state NMR characterization of a model anion exchange membrane. The stage is yours.
So, thank you for your kind introduction, and good afternoon to everyone. As already said, I'm Andrea Giovannelli, and I'm a PhD from the University of Pisa. And during this short presentation, I will show you some results that I have obtained on the solid-state NMR characterization of a model anion exchange membrane. First of all, I'd like to introduce the field of anion exchange membranes. Basically, anion exchange membranes are, as the name suggests, membranes that are based on, usually on polymeric materials, and that are able to conduct anions while completely blocking cations. This particular property is quite interesting in nowadays research because it can be used in sectors related to the green energy production and the green hydrogen production and its conversion back into energy. The membrane that we have studied is commercially known as Fumasep, and we have chosen this material because it shows quite high performances in terms of chemical resistance and conductivity. And it's also quite cheap. It's in fact one of the cheapest available on the market. These two characteristics make this membrane a perfect benchmark because properties of newly synthesized membranes are usually compared to the properties of this one. This material is composed by two polymers. The first is the FAA3, which is based on polyphenylene oxide, functionalized with an undisclosed quaternary ammonium group. And this polymer is the one that gives the ion conductivity property to the membrane. The second polymer is a polyketone, specifically polyether-ether ketone, and it's included in order to improve mechanical properties and dimensional stability of the membrane. We used the solid-state NMR to study this material, and here I have reported the picture of the spectrometer that we used. And we mainly focused on three aspects concerning the structure, so the local connectivity of atoms, the phase separation between the two polymers, and also we tried to investigate the formation of ionic channels upon hydration. First of all, we started by recording some proton spectra. They are quite wide, but if you are not used to solid-state NMR, they may look so, but in reality, it's a quite good spectra, even if it's like large 10 ppm. And you can clearly distinguish two domains, one of the aromatic protons and another one of the aliphatic protons. Aromatic protons are present on both polymers, while at the same time, aliphatic protons are only present on polyphenylene oxide. We also see another peak, quite sharper, which probably belongs to residual water adsorbed in the membrane. And it's quite interesting to see that the two polymers, the two proton types show a different relaxation behavior, and we are going to investigate it later in a consecutive slide. We also studied the presence of fluorine in order to see if the functionalizing agent contains any fluorine. And we identified the presence of one peak. However, after some research, we understood that this is in fact as a fluoroisopropanol. And this means that probably this solvent is used in the preparation of this membrane, and no fluorine is present on the polymer itself. We then tried to characterize, to measure relaxation times of protons in order to understand the phase separation between the two polymers. And we have done this using an inversion recovery cross-polarization sequence. So basically, we cause the relaxation of protons, and then we transfer the magnetization to carbons. So we detect from carbons, but the integral of carbons is dependent on the relaxation of the neighboring protons. And the result is like the one shown in the video, where we see that different signals invert at different time delays during the relaxation. In fact, if we consider, for example, the ketone group, which is only present on the polyether-ether ketone, we see that neighboring protons relax with the mono-exponential behavior with a relaxation time of about 2.4 seconds, while at the same time, if we consider the aliphatic region, which is only present on polyphenylene oxide, we get a much shorter relaxation time. This is an indication that the two polymers are well separated into two distinct domains with a dimension, of an average dimension of at least 10-15 nanometers. This is also confirmed by the fact that if we integrate the aromatic region, we get a perfect B-exponential behavior with the two previously found relaxation times. From proton, we then moved to carbon, and we performed many different cross-polarization spectra and at-core maps in order to identify all different signals and assign them to the relative carbon on the structure of the two polymers. We also identified the region where carbons that are directly bound to the quaternary ammonium group resonate, and we also tried to investigate it more deeply using direct excitation on carbon coupled with relaxation times of carbon. This type of analysis allowed us to get a first hypothesis on the structure of the functionalizing agent, which we believe is of the type dimethyl dialkyl ammonium, with the two alkyl groups that are probably different one from the other. Last but not least, we hydrated the membrane with deuterated water, and we performed this in a controlled environment in order to then study the adsorbed water with deuterium NMR. And what we see here is the presence of this peak with a weird shape, and it's composed by a center band, which probably belongs to bulk water. But we also see two side shoulders, which in solid state NMR are usually known as a peak doublet, which is typical of quadrupolar nuclei. And we believe that this is an evidence of the formation of the ionic channels, because the peak doublet is usually present when the mobility of the water is restricted. So we believe that those two shoulders are the walls of the ionic channels, while the central peak is the bulk water inside the channel. We also tried to cool down the sample and to heat it up. And as it can be seen, from cooling it down, we lose completely the resolution. But if we heat up the sample, we get a much sharper central peak, and we can distinguish the peaks doublet way better. And so with this, in conclusion, we studied the phase separation in the membrane, and we determined that the two polymers are well separated into quite big domains. We also gained some insight on the structure of the functionalizing agent, and we also studied the formation of ionic channels using deuterium NMR, and we are going to further explore this side by simulating the pattern of deuterium in order to understand the mobility of the restricted water. And with this I have concluded. I'd like to thank the Smart Polymer group of the University of Pisa and the SSNMR group of the University of Pisa. And I thank you all for your attention.
Thank you again. Are there any questions? Okay.
Thank you for the presentation. For me, it's just a curiosity because I don't know very much about NMR solid state. But in the last slide, you show that when you cool down the sample, you lose the double doublet. So the temperature is lower than the melting temperature of water. So does it mean that when the water is frozen in the solid state, you lose the differences between the bulk and the water close to the channels, or it's just another effect?
Okay, so this is an extremely good question, and in fact it's one problem that we are trying to tackle down. And the fact is that, as you can see, the peak is extremely wider. I mean, it goes from a few ppm to more than 50. So we believe that when the water freezes, it freezes in a disordered way. So the peak becomes wider, and we cannot be sure if the peak's doublet is still under the peak. Maybe it's still there, it's just the peak too broad to see it. And we will try to understand if it's still there, but in theory it should.
Okay, I have just a quick question. So, do you think you will use other techniques to characterize these membranes?
Okay, for this membrane, maybe we will perform some thermogravimetric analysis, and we are also probably going to take some SEM images. But our concern with this membrane is mainly on solid-state NMR, but just because we want to use this membrane to build a protocol for the analysis of newly synthesized membranes. So yeah, probably not so much.
Okay, thank you. So we can thank again Andrea. Okay, so the next speaker is Giorgia Giusti. Okay, with their work about cellulose hydrophobization for beverage packaging applications.
Hi everyone, I'm Giorgia Giusti and I'm a first-year PhD student at the University of Bologna with a scholarship co-funded by the Italian company SACMI. Today I would like to talk to you about my PhD project that regards cellulose hydrophobization for beverage packaging applications. SACMI is specialized in the development of technology for the packaging, food and ceramics industries. Regarding the packaging sectors, SACMI is really caring about the ecological impact of its products and is trying to substitute synthetic plastics with more sustainable and renewable resources, also due, of course, to the well-known environmental problems of synthetic plastics. Thus, SACMI is wishing to propose a completely free, plastic-free solution, and for this reason he has decided to invest on cellulose. Indeed, cellulose has a lot of advantages that make it a very promising choice to gain this goal, because, for example, it is renewable, biodegradable, and widely spread in nature. So, however, the industrial application of cellulose has two main problems: processing and hydrophilicity. For the first one, cellulose cannot be processed at the same time of traditional thermoplastics because it degrades before melting. SACMI has already found a solution by developing a technology to mold dry cellulose fibers and giving them the desired shape. In the slide, we can see the starting materials they used are very fluffy and cotton-like materials compared to the final object they obtained, are very rigid and complex materials. In this case, is a cellulose-based caps for bottles. Moving on the second problem, the chemical structure of cellulose fibers, showing many hydroxylic groups on the surface, allow them to attract and hold water molecules through hydrogen bonding. Moreover, the presence of a lot of pores and void spaces increase and improve its wetting behavior. Several methods have been proposed in the literature to modify the cellulose to make it more hydrophobic, and this method can be subdivided into two main families: the chemical modification and physical methods. For the first one, there are a lot of methods proposed in the literature to chemically modify cellulose. For example, the use of sizing agent, the click chemistry, or esterification, and so on. Moving on the physical methods, the most interesting one is the plasma methods because these are eco-friendly and dry methods and also scalable. Among these numerous approaches proposed in the literature and with a focus on the scalability and sustainability of the process, we have decided to follow two main routes: chemical vapor deposition approach and the cellulose surface activation. In our CVD approach, we have decided to perform a very simple experiment by placing the cellulose substrate with a liquid hydrophobic silane inside a sealed glass container. And these closed systems were positioned in an oven for different times, from a minimum of 3 hours from a maximum of 1 week, and different temperature, 20, 55, and 100 degrees. Then these cellulose substrates were hot pressed, and before further characterization, some of the sample have been further treated at 120 degrees for 1 hour to see if this step has a key role in our modification, because theoretically the thermal post-treatment has to promote the adhesion of arganesilane onto the cellulose surface. First of all, water contact angle measurement have been carried out to observe our modification, to observe our cellulose substrate, because it's the simplest method to see if the modification has been successful. So we have decided to collect more than 1 point for each cellulose sample to see the reproducibility of these results. And then we have decided also to run the measurement for more than 1 minute to observe the stability of our modifications. In this slide, we can see that even though the experiment run at 20 degrees isn't enough to chemically modify cellulose, the higher temperatures are promising, and we have obtained hydrophobic cellulose substrate only after the stable hydrophobic cellulose substrate only after the thermal post-treatment, which means that is a very significant step of our process. Moreover, we can see in this slide that the comparison between an image of cellulose and a CVD modified cellulose, and it's clear that there is no formation of a film, but probably we have modified single fibers. Moving on the second interesting route, the modification of cellulose is a method to modify cellulose to improve its reactivity. For our purposes, we want to couple this particular activation with a second hydrophobic method to make cellulose more resistant to liquids for obviously packaging applications. We have decided to try two very different routes. A wet method by using tannic acid, where tannic acid is a particular polyphenol that is commonly found in various plant species. We have only done the preliminary studies and only performed the preliminary results and characterization, but this route is very interesting, and we want to continue with this process. Then we have decided to try a dry method by using atmospheric oxygen plasma. Indeed, the exposure of cellulose substrates to this particular cold plasma leads to the formation of particular functional group that on the cellulose surface, facilitating the adhesion of other materials. To conclude, I have decided to try two very different methods to chemical or physical modify cellulose. And for the first one, we are building a particular apparatus to improve and better control our experiments and to improve the kinetics of the process. Furthermore, we have decided to extend our characterization techniques, coupling the more common one like infrared spectroscopy and the water contact angle measurement with the more sophisticated one like, for example, XPS. I would like to thank my supervisor, Chiara Gualandi, and the organization committee to give me the opportunity of being here, and thanks you all for your kind attention. For any cues, I'm here for the discussion. Thank you.
Thank you again, Giorgia. Are there any questions? Okay, if not, I have a quick curiosity. So are you planning to use other hydrophobic molecules like tannic acid to modify your cellulose packaging?
Okay, actually tannic acid is not an hydrophobic agent because I use it to activate the surface. So the water contact angle, there is not an improvement of the water contact angle. But with tannic acid, I can use basically all type of hydrophobic agent because I can use, for example, the chemistry of thiol-heme reaction or also esterification. But I can use also a dry method, like another plasma, after the plasma activation, I can use a plasma with an hydrophobic agent like a DMSO, or then a CBD also. The first, my first promising routes.
Okay, thank you. Okay, we can thank again Giorgia. Now it's the turn of Valentina Lamatta. Sì, è quello davanti. With their talk about life cycle assessment of tires, the role of the production phase.
Prova. Okay. Good afternoon, everyone. I'm Valentina Lamatta. I'm a PhD student on my first year at the University of Naples Federico II. And today I would like to talk about the importance to make a life cycle assessment on tires and underlining the role of the production phase in this kind of modeling. So, let me briefly introduce what is life cycle assessment. It is a powerful analytical tool to evaluate the environmental impact of a good or a service during its entire life cycle. I mean, it starts from the extraction and the processing of raw material, meaning the cradle of a product, to the grave of the product itself, meaning the disposal phase. So, by evaluating the resources consumption and the waste production, and also the emissions into the environment, we are able to assess the environmental impacts following this standardized procedure, and then we are able to assess which product is more impactful than another. So we can promote an informed decision making. For my PhD, the life cycle assessment will be done on the pneumatic tire production phase. The pneumatic tire is a very, very complex product. It has at least 10 ingredients categories, and every category has different compounds, different chemical ingredients, and all the chemical ingredients can form different compounds, which have to respect different properties based on the position into the structure of the tire. Regarding the present literature, I start the study of in my first 6-year PhD by studying this review, which collects all the studies on LCA analysis on the pneumatic tire. And there are more or less 16 studies. And as we can see in this graph, most of them are focused on the end-of-life treatment of the tires, when only 15 of them, including also the raw material extraction phase and the production of the tire itself. So, these two phases are very, very impactful. In fact, I select these two papers to show you. The first one is a Michelin study. It reports this results in 3 different impact categories for 3 different phases of the life stage of the tire. And we can say that the percentage of the impacts by summing the raw material production and the tire manufacturing impacts, this sum is weightier, is heavier than the impact of the end-of-life phase. So we can say that the cradle is as important as grave. And moreover, I report this second study, which proposes the substitution of guaioli rubber tire, which is a bioderived rubber, to the synthetic rubber of the conventional tire. And as we can see in this bar graph, which reports the material composition of the 2 different types of tires, by changing only one component means a total redesign of the production phase. So I think that at this point is clear and evident the strictly link which exists between the raw material production phase and the tire manufacturing phase, and also the need to make a LCA analysis with that detailed and accurate modeling of these 2 phases. So in these first months, we started with this first step. We modeled a comparative LCA analysis for a lab-scale elastomeric 3D compound production. In these studies, we included the raw material production phases for rubber and some chemicals, and then the mixing and the vulcanization of a rubber vulcanized plate. So then we made a comparison between 2 types of compounds, both based on elastomers and chemicals, but the first one has a bio-based resin and the second one a petrol-based resin, where the resin is usually used in tire to modulate the properties of the rubber. So this simply map translated into LCA modeling environment assumes a bit complexity. On the left side we have raw material production phases, and on the right side the compound production. But since the production of the 2 compounds were made at the same conditions and timing, we can say that the only differences in terms of impact will be due to the second mixing process, meaning the process where the resins are fed. So the differences will be due to the different electricity supply to this process, and of course caused by the raw material production phases, which are different by passing from the petrol-based resin to bio-based one. So regarding the electricity supply, we found that the bio-based resin compounds consumes more than the petrol-based one. It results with an higher impact for the bio-based compounds. As we can see also in these 2 bar graphs, where I reported these 2 impact indicators. The first one estimates the toxicity for the human health, and the second one estimates the greenhouse gas emissions. In both cases, the bio-based compounds has a higher impact, but if we look at the torque time curve of the second mixing process, of course, we see that the petrol-based compound mixings probably has a slip during the mixing process. So since the LCA modeling will be done on compounds with the same performances, probably this second mixing process will be revised and the timing changed. So regarding the raw material production phases, due to LCA databases limitations, there was the need to select some proxy processes to substitute the racing production processes, where these proxy processes are processes that have similar impact to that we want to substitute. So we select 3 different proxy processes for the petrol-based racing production process, and other 3 for the bio-based one. So we made 6 different modeling, and then there are the results. I report first this indicator, which estimates the consumes of non-renewable resources, and of course the petrol-based sources consumes more than the bio-based one. But I reported also these 3 impact indicators, where the first and the second were previously seen, and the last one estimates the toxicity on the terrestrial soil. And in all 3 cases, we see that there is a high variability in selecting the bio-based source, but in our case, for example, the rosin size is the product more similar to the bio-based resin that we are using into our system. And for the 3 cases, the bio-based, this kind, the rosin size has a higher impact than all the petrol-based compounds, all the petrol-based sources that we have selected. So these are unexpected results, which highlight the need of a vigorous modeling for an LC analysis. And there is the need of a deep investigation before using a bio-based source for a real sustainable tire. And for future developments, I will research obviously on more accurate data to cope with this limitation of the databases. And obviously, there will be the scale up to a real system. In fact, this is what awaits me. A huge number of flows and production line. So good luck to me. Okay, thank you for your attention.
Thank you, Valentina. Are there any questions? Okay. So it's a very hard project.
Yes.
So I was wondering if, I mean, in the end, you want to find, you have to scale up all your
Yes.
project, but also, do you think that it's really possible to use a bio-based resin, or because it seems like it is not.
What I was meaning with this presentation is that we can use all kinds of sources, okay? Bio-based or petrol-based, but before make the decision, we have to do a life cycle assessment analysis to understand which is better than another, you know?
Okay, thank you. Okay, we can thank again Valentina. So the next speaker is Erika Laguzzi. Okay, the stage is yours.
Thank you for the kind introduction. I am Erika, and as many among us, I am a first-year PhD student, and today I'm here to talk to you about my project. What do I do? I synthesize vitrimers. But what are vitrimers? We are talking about a class of covalent adaptable networks, which is a type of polymers that, to be honest, are too good to be true, because they merge together the mechanical properties of thermoset material with the ease in reprocessing of the thermoplastics. And how can this material do this? Through the incorporation of dynamic covalent bonds inside their network. These bonds can respond to a stimulus, think about the temperature, think about the light, and they can break and exchange, giving the network the mobility that is necessary in order to have a topology modification of the network. How can you synthesize this kind of networks? There are many different syntheses, but we decided to focus on the beta amino ester chemistry. Beta amino esters can easily be synthesized through azomical addition between an amine and an acrylate. And the dynamic feature, first I want you to focus on the fact that the beta amino ester, it's not working, okay, the beta amino ester is the cross-linking point of my network. So the dynamic features relies on both an associative and a dissociative mechanism. The dissociative mechanism is because the azomical reaction is reversible, so we can shift the equilibrium can shift back to its initial reagents, while the associative mechanism relies on the fact that the ester can undergo transesterification, thus giving this sort of exchange in the group that is linked. So this is the theory. Experimentally, the synthetic approach was a little bit different because our lab collaborates with Elantas, which is a company that produces wire enamels, and they granted us the use of their industrial monomers. So we are working with a bifunctional amine and a mixture of bifunctional methacrylates. In order to obtain the network, it's very simple. I just need to mix the reagents together and heat them up. So I have the network and I have everything I need inside the network in order to have a dynamic exchange. Because I do have the beta amino esters that can undergo dissociation and also the hydroxy functionality built in the network. I do not need to add any additional reactants. I do not need to add a catalyst. Even if transesterification usually requires one, I do not need it here because I have the beta nitrogen that gives me an activated ester. So our first approach was to play a little bit with the molar ratio between the methacrylates and the amine. As you can see, we can reach the higher glass transition temperatures with the 1 to 0.5 ratio, methacrylates to amine. And to the company I'm working with, a higher glass transition temperature was more interesting. So we keep doing the synthesis using that parameter. Now we had synthesized the material, which is here. This is my hand. And we need to establish the fact that we, in fact, formed correctly the dynamic network. And this can be done through stress relaxation experiments. In this kind of experiments, I apply a constant strain and I measure the stress. If the material is a thermoset, I will observe no decreasing in the relaxation modulus. And I would like to remind you that technically a vitromer is a cross-linked material. So in theory, it should behave like that. But thanks to the dynamic bonds that I incorporated inside, I expect a behavior more like a thermoplastic. So a complete stress relaxation. And thankfully, it does. I can see complete stress relaxation. My trigger is simply temperature, so I just need to perform my experiments at different temperatures, and the temperature gives my dynamic bonds the energy that is required in order to make everything dynamic. The last data I would like to show you is that the contact with water tests.
because the company was also interested in this kind of behavior. So I basically drowned my sample in water, left there in the lab for room temperature for many days, and I monitored the glass transition temperature, and as you can see, it decreases. So what's happening? The first thing that came up to our mind was, okay, let's heat the sample up again and see what happens. Well, we were able to recover the initial glass transition temperature. Thus, we think this suggests us that water can act as a plasticizer and does not degrade my sample. So this is what I've shown you this far is not much, but it's honest work. So I've just started. This is just explorative. We're still having a lot of trial and error process here, and we do not really have a target for defined characteristics of our material. And we have many more tests that we want to perform, but I can do anything. I can do everything on my own. So I will stop here and thank everyone for supporting me, the company for sponsoring the project, and of course you all for your attention.
Thank you, Erika. Are there any questions? Okay, there.
Hi, Erika. Thank you for the presentation. I was wondering, you have a V-trimmer.
Yes.
You observe a decreasing in your DMTA analysis, but as you know, the V-trimmers have a particular range of temperatures where the network turns dynamic. Do you deeply study that aspect during your analysis?
No, we haven't, because we have many problems. For example, for DMA tests, till now, my sample, it breaks during the measurement. So I'm still tuning the synthesis in order to measure that.
Nice.
Thank you for the question.
Are there more questions? Okay, if not, we can thank it. Ah, sorry. Sorry.
Thanks for the presentation. And maybe I missed that. I saw that you showed the work of Dupré for the question of the mechanism of associative dissociative. I was wondering if you have done some kind of, because he for this work used model molecules for assessing if it's associative or dissociative. You have done something like that for your work to assess if your mechanism is associative or not, or you are planning to?
Thank you for your question. I haven't yet, but the reactants arrived, I believe, last week in the lab. So I will perform that as soon as I get back. Thank you.
Okay. Thanks.
Okay. Are there any questions? Oh, yes.
Thank you for your presentation. The question is, thanks to the associative or dissociative mechanism, can you recover part of your polymer during the, for example, oligomers or monomers, thanks to the...
We still have to perform reprocessability tests. I've tried to do self-healing, but till now I was not successful.
Okay.
So, thank you for the question.
Okay, I think there are no questions, so we can thank again Erika. Now it's the turn of Martina Martuscello. Showing a work about all polymer-based mechanochromic distributed Bragg reflectors.
Thank you, Benedetta, for your nice introduction. And good afternoon, everyone. I'm Martina Martuscello, and today I will tell you something about my work on mechanochromic materials. So, there's growing interest in mechanochromic materials, so in materials that changes color when subjected to a mechanical stimulus. In fact, they can find very interesting applications in different fields, going from structural health monitoring to medicine, for example. In fact, non-destructive mechanochromic sensors have been reported to assess, for example, dangerous deformation in buildings, and in medicine instead they are used to control the muscle contraction. And okay, as you know, scientists get used to imitate nature, okay? And if we think about one animal that changes color, the most famous is a chameleon. And that's why in their skin there are nanocrystals of guanine that arrange periodically to form nanostructures that we all know as photonic crystals. Photonic crystals are so nanostructures composed by two materials with different refractive indexes that arrange periodically to form a dielectric lattice extending in 1, 2, or 3 dimensions. And in our work, we decided to use the most easy form of photonic crystals that are distributed Bragg reflectors, so one-dimensional photonic crystals that are also known as dielectric mirrors. That's why, since the periodicity of the crystals is of the same order of magnitude of the wavelength of the visible spectrum, when the light interacts with that structures, a combination of reflectance, transmittance, and diffraction of light causes a perfect wavelength range to be reflected and not transmitted from the structures. This particular range is also known as photonic band gap and is represented by a pronounced reflectance peak. To realize our sample, we decided to use spin coating, that is an easy and reproducible technique in laboratory scale. So after the deposition of a reinforcing thicker layer of a SAB scopolymer, I decided to go with the construction of the photonic crystals itself, made by the alternation of thin films of a perfluoroelastomer and a styrene butadiene copolymer. When completed, our samples looks like that. You can see a structural color, but you can see also some inhomogeneities due to the low adhesion between the materials. But despite that, we can still see 3 band gaps, 3 orders of the PBG, represented by the 3 pronounced peak in the reflectance spectrum. So, observing the Bragg-Snell law, we can see that the position of the wavelength of the PBG is related to different parameters, but the most important for our purposes is the periodicity, so the thickness of the layers, and decreasing the thickness of the layers by stretching the structure, we can see a blue shift of the wavelength of the PBG. Baer and his colleagues theorized the correlation between the wavelength of the PBG and the strain, with one only parameter, that is the original wavelength of the PBG. So we decided to insert our data and to try to plot them with this equation, and we obtained these trends. Okay, in order to see if our samples are comparable with these trends, we performed an optomechanical assessment combining a reflectance setup with an homemade extensimeter, and we obtained with the results this contour plot showing the wavelength versus the strain, and in color scale the normalized reflectance. The band gap is represented by the blue band on a red background, and we can see that our data are comparable with the theorized one. With this setup, was also possible to obtain the behavior of these materials in the contraction cycle, and we can see that the response is very immediate and is quite reversible. In fact, at the end of the entire cycle, so elongation and contraction, the wavelength of the PBG comes back to quite the original position. It was also possible to measure the mechanochromic sensitivity that for our sample showed that with a 1% of strain, the wavelength shifts of 1.6 nanometers. So in conclusion, I can say that we obtain strain-sensible mechanochromic photonic crystals with an immediate and reversible chameleonic behavior. Now we are working to improve the optical quality of these structures in order to obtain then elastic microcavities. And in the next future, we hope to add to our structures new materials in order to find new applications. I would like to thank my supervisor and professor for their help, and my colleagues, and you for your kind attention. Thank you.
Thank you again, Martina. Are there any questions? Okay.
Thanks for your presentation. I have a curiosity. In your one-dimensional crystal structure, the width of the layers of the polymer influence the mechanochromic response or not?
You mean from the point of view of the mechanical stress, or from the photonic point of view? Because the thickness of the layers has a role in the optical response. In fact, the thickness is directly a parameter that influences the wavelength of the PBG. But from a mechanical point of view instead, maybe a thicker layer can increase or reduce the mechanical behavior. So maybe the color is related also to the capability to extend the structure.
Okay, I'm satisfied. Thank you.
Thank you.
Are there any questions? Okay, if not, I have just a quick curiosity. You showed a few applications of these materials. Will you be focused on one in particular, or you?
I think that I will concentrate on the structural health monitoring applications.
Okay, thank you.
Thank you.
Okay, we can thank again Martina. The next speaker is Monica Milani, showing her work about adhesion enhancement in CFRP composites via topological entanglement.
Okay, so good afternoon everybody. I'm Monica Milani from University of Parma, and today I'm showing you my results on the synthesis and mechanical properties of this new adhesion enhancement in CFD composite via topological entanglement. So what are composite materials? Composite materials are a combination of two or more phases with increased properties in respect of those of these single components alone. So carbon fiber reinforcing materials are composed by a matrix, an epoxy-based matrix, and are reinforced, that is commonly based on carbon fibers. So these kind of materials are very lightweight and possesses high mechanical properties, so they are widely used in automotive industries and aerospace industries, but they suffer from the lamination between the plies of the carbon fiber, and they are not recyclable. So the delamination can occur in 3 different ways. The first way is the opening delamination. The second way is in plane delamination, in plane shear. And the third way is out of plane shear. So our solution to tackle this problem is to functionalize a commercially available phenoxy resin that is compatible and physically miscible with the commonly used amine-cured epoxy resin, the carbon fiber composites, with the iodine molecule. The iodine molecule is an organic molecule that can dimerize within itself, forming 6 hydrogen bond array. So the mechanical stress dissipation is achieved thanks to the penetration of the functionalized phenoxy resin with the iodine molecules and the formation in situ of the iodine dimer. But what is the topological entanglement? The topological entanglement consists into the penetrating of the functionalized phenoxy resin into the epoxy network, and then the formation of the iodine dimer. The increase of the mechanical properties of the materials is achieved thanks to the subsequent breaking of the 6 hydrogen bond of the iodine dimer. So we synthesized this kind of adhesive by functionalizing the low molecular weight phenoxy resin with the iodine molecule, adding a catalyst in the MSO dry. The adhesive were tested by proton NMR, characterized by proton NMR and by nitrogen elemental analysis. We tested the mechanical properties of this new adhesive via single upshare test. We tested both the phenoxy resin alone and the functionalized phenoxy resin with 5, 10, and 15% of the iodine molecule. And both of these kind of adhesive were dissolved in the same solvent, in the same mixture of solvents, chloroform and hexafluoroisopropanol. So once the adhesive were applied to the composite, we placed the specimen under vacuum, and then the cooling cycle was in autoclave for 90 minutes at 135 degrees at 6 bar. So the single upshare test result showed an improvement of the shear strength of the material by the 14% by using the simple phenoxy resin, not functionalized. This is thanks to the physical entanglement, so the simple diffusion of the polymeric chain of the phenoxy resin into the epoxy network. By using the 5% of phenoxy resin functionalized with the 5% of iodine, we achieved a 38% of the improvement of the shear strength of the material. This is thanks to the topological entanglement, so the subsequent breaking of the 6 hydrogen bond array of the iodine molecule when the stress is applied on the material. By adding more iodine molecules on the resin, so increasing the percentage of functionalization, we didn't observe an increase of the shear strength of the materials. Consider also the deviation standard of the measurements. We also measure the peak load of the material. So in respect to the reference, we observe an increase of the peak load of almost 20% by using the simple phenoxy resin. By using the phenoxy resin functionalized with increasing percentage of the iodine molecule, we reach the 30% of improvement in the peak load of the material. So in conclusion, we synthesized and characterized by proton and elemental analysis this new kind of adhesive promoters via topological entanglement, and we tested also their mechanical properties by single upshare test. The DCB and the ENF test are currently ongoing in our research group to test also the mode 1 and the mode 2 of the lamination. So I want to thank the organization committee, all my colleagues and you for your kind attention.
Thank you, Monica. Are there any questions? Okay, if not, which could be a possible application of these composites?
These kind of composites are useful in automotive industries for increasing the tenacity of an epoxy resin used for as a matrix for a carbon fiber. So it's used in cars where you need a very high tenacity resin.
Okay, thank you. Okay, we can thank again Monica. And the next speaker is Daniele Natali with his presentation about semi-crystalline polymeric networks as tailored shape memory materials.
Sorry. I was saying I am a PhD student from University of Bologna, and I would like to introduce you my work on semi-crystalline shape memory polymers. So, what are shape memory polymers? Are a class of smart materials that are able to change their shape in a predefined manner in response to a proper stimulus. They are bringing great innovation in many fields, for example, the biomedical, in which they are being used for different applications, but also in soft robotics as soft robotic actuators. We can have different stimuli to activate our shape memory properties with a polymeric network. The most common is the heating. So of course we need a thermal switch. So for example, a transition with high modular variation, of course a glance transition temperature or maybe a melting temperature, and also the presence of physical or chemical net points. We can have so mainly 4 categories of shape memory. Oh, we have, sorry, the video is not perfect working, sorry. We will focus on semi-crystalline polymeric networks with chemical net points. We can have different shape memory effects. The most common is the so-called one-way, in which a material can retain a temporary shape after a proper programming cycle, and then it can recover the original one when the proper stimulus is applied. During the programming cycle, we have that the material passes from a low change mobility state at low temperature to a high change mobility state above its transition temperature. Here, a stress is applied to induce a deformation and temporarily oriented the macromolecule change, leaving the material in an entropic unstable state. If we cool down the material, now we fix the temporary shape, and removing the stress and heating again the material, we recover the original shape thanks to the presence of chemical net points and to the entropic driving force. This is an irreversible mechanism, but with semi-crystalline polymers, we can also have reversibility. So, for example, the two-way under continuous applied stress. We have already seen that we can temporarily orient the macromolecule change during the programming cycle. Now, if we don't remove the stress while we are cooled down, the material exhibits the cooling-induced elongation. It means that while the macromolecule is cooling down, it crystallizes under stress, increasing its tensile deformation. Maintaining the stress and heating again the material, it will recover the deformation because it can contract, and the effect is called melting-induced contraction, but it can recover just the deformation occurred during the crystallization since the stress is still applied. This mechanism is reversible, so upon cooling and heating cycles, we can switch the material from 2 different shapes by maintaining always a stress applied. Interestingly, it has been also demonstrated that the two-way stress-free mechanism can achieve so without any external stress, but we need 2 different domains in our material. So, for example, 2 different semi-crystalline domains. One must act as skeleton domain that is not affected by the changing in the temperature and must exert an internal stress on the actuation domain. That is the switchable part of the materials and must be able to reversible melt and recrystallize on the skeleton domain. So, after the programming cycle, we obtain the first temporary shape. If we melt just the actuation domain, the material contracts, obtaining a secondary temporary shape that now is able to undergo two cooling-induced elongation and melting-induced contraction cycles thanks to the internal stress exerted by the skeleton domain. So the objective of my works was to prepare a new material with two different semicrystalline domains in order to try to obtain reversible shape memory properties, so of course stress-free or even under stress. I choose to use polybutylene succinate and polycaprolactone as my two semicrystalline domains, since they are two semicrystalline polyester with well different and separated melting region. So I started from the synthesis of polybutylene succinate diol with a classical two-step polycondensation. After that, I functionalized both PBS and also a commercial polycaprolactone diol with a methacrylate isocyanate moiety in order to obtain terminal groups suitable for radical cross-linking reaction. I could prepare so different blend with different composition of my polymers by melt blending. I prepared some films, and in the presence of the photoinitiator, I could photocure my samples, obtaining my two semicrystalline polymeric networks with a chemical cross-link, of course. In this case, the high melting PBS should act as the skeleton domain, while the low melting PCl should act as the actuation domain. So, according to literature and from the thermal analysis, we can see that increasing the PCl content in the network is not always easy to detect a crystallization need peak of PBS, but it's not a problem because in the second DT scan we always manage to have a neat melting peak of PBS, meaning that you always manage to crystallize. That is mandatory for the shape memory properties. From first trials, we have seen that the network with 25% of PBS content seems to be the best promising for shape memory applications. And I would like to show you some first results that I achieved with this material, hoping that the video is in a good way. So, at first, I want to show the one-way mechanism, but since we have two different semicrystalline domains, we can fix two different temporary shapes on our material. So we can, first of all, use a first programming cycle, deforming the material above the melting temperature of PBS and then cool down, obtaining the first temporary shape. And then we can repeat the same process, but just above the melting temperature of PCl. And so we can fix a secondary temporary shape. Now, the original one can be recovered by melting one at a time the two different semicrystalline domains. So from the secondary temporary shape, if we melt just the polycaprolactone phase, we can recover the first temporary shape. And of course, if we melt also the PBS domain, we can recover also the original shape. I achieve also quite good results also for the two-way stress-free mechanism. So I fixed a first temporary shape in a classical way above the melting temperature of PBS. Then I could just melt the polycaprolactone phase. So I obtain a secondary temporary shape that now is able to undergo to cooling-induced elongation and melting-induced contraction thanks to the internal stress exerted by the PBS domain. So we now have the first contraction of the material, and so we obtain the secondary temporary shape. Now, just cooling down the actuation domain, we obtain this shape that can reversible pass from this one by heating again. Of course, it's reversible, so cooling and heating again, we can switch in a reversible way from two different shapes, like that. Of course, if we melt the PBS phase, we will recover also the original shape. So, to end my presentation, I just want to tell some words about the ongoing studies. I show you just some qualitative results on my materials, but of course we are studying also with dynamical mechanical analysis, that is the classic analysis for shape memory properties. So in this way we could study also under stress or stress-free mechanism, and we can have some important data such as the strain occurring during the cooling-induced elongation and the subsequent recovery. We can evaluate the reversibility of the process and understand the stress needed to activate the shape memory properties. Moreover, we can also understand which of our components, of our networks, has the best composition to the best shape memory properties. So I just want to thank you for the attention and all of my colleagues and friends that are here. So thank you.
Thank you, Daniele. Are there, okay, there is a question.
So thank you, Daniele, for your nice presentation. Just a curiosity about this heating and cooling cycles of your materials. How many cycles you can perform?
I haven't tested how many cycles. In theory, you can do how many times you want until the materials break. So I haven't tested how many times you can do that, but it's not the problem of the reversibility. It's just the problem when the material breaks down for mechanical resistance. So in theory, you can do whenever you want.
Okay, thank you.
Thank you.
Are there any questions? Okay, I have just one. I could have missed the point, but why did you choose PBS PCL as the best, 2575 as the best sample?
Okay, thank you. No, just because we have just tried some quick mechanism, and so first trials, just by qualitative way, it seems to be the best responsive for this application. But of course, we need the DMA test to prove that this is the best. Maybe we can find out that it's not the best. So at the moment, this is the situation. We are waiting for the results. Thank you.
Thank you again, Daniele. So the next speaker is Rosita Gentile. With their work about design and synthesis of mechanophores for self-diagnostic V-trimmers.
Good afternoon to everybody. I am Rosita Nicolella Gentile from University of Parma, and today I will talk about And today I will talk about the design and synthesis of mechanophores for self-diagnostic V-trimmers. Covalent adaptable networks, also called CANs, are a particular class of material that presents covalent bonds that are dynamic under specific stimuli, such as heating. They can be divided into dissociative and associative CAN. In the first, there is the bond breaking that precedes the bond formation. So the bond breaking leads to cross-link cleavage. In the associative CAN, the bond breaking and the bond forming take place in a single reaction. So there is the retention of cross-linking density. I focus my attention on associative CAN that are also called V-trimmers. V-trimmers are a peculiar class of materials that behave like thermosets at their working temperature, but can be reprocessable like thermoplastics at a higher one. This behavior is due to their chemical structure that is characterized by associative covalent adaptable networks. Bonds can be broken and restored at high temperature, thus allowing the reshaping of the material. For all the material in which high structural identity integrity is required, the possibility to detect an early stage of damage can represent a precious tool. Here I report work on my research group in which it was used an host-guest approach to detect a microdamage. This host-guest approach was inserted in epoxy thermosets, and it was demonstrated that under mechanical stress there was a disassociation of the complex and the fluorescence switches on. But it has some troubles because it is in epoxy thermosets that isn't recyclable, and the probe for stress detection isn't reversible. So the aim of my work is to obtain a recyclable vitrimeric material, more a reversible probe for stress detection. To do that, we use the mechanophoric approach. Mechanophores are molecules that undergo structural changes triggered by a mechanical force. A particular class of mechanophores are represented by mechanochromophores, in which the structural changes is accompanied by a change of color. Mechanochromophores are divided into radical-based and isomerization-based. In the isomerization-based, the molecule has a spirojunction, that is a label bond, and when the molecule is functionalized and linked to a polymeric matrix, under mechanical stress, there is the breaking of this label bond and the process of ring opening. The important thing is that the processes of ring opening and ring closure are reversible. In literature are known different types of mechanophores, isomerization-based. I focus my attention on spiropyran and naphthopyran, and for time reason, I will only talk about the naphthopyran.
So, as I've said before, the aim of my work is to obtain a recyclable vitrimeric material, more a reversible probe for stress detection. But how can we do that? Functionalizing the mechanochromophores with the silly letters to work as a cross-linker in silly letter vitrimers. I have chosen the matrix, the PEMA matrix. PEMA is polyethylene copolymerizide with hydroxyethyl methacrylate. So, naphthopyran. Naphthopyran is a molecule that has two different moieties. We have the naphthalenic and the indolic one. In position 3 there is the label bond, and when the molecule is functionalized in position 5, under a mechanical force, there is the breaking of this label bond, and the molecule convert into merosaninic form that has an intensive orange color. In this study, they demonstrated that only when the molecule is functionalized in position 5, there is the conversion into merosaninic form. So I decided to synthesize this naphthopyran that isn't known in literature. I used a convergent synthesis, and I obtained the intermediate 4 with several steps, and in only one step the intermediate 5. Intermediate 4 and 5 were reacted to obtain an naphthopyran with an yield of 65%. Then I functionalized this molecule with isocyanate silane to introduce on the molecule silly letter groups to work as a cross-linker. Then I tried to prepare a PEMA film. In particular, I dissolved PEMA in orthodichlorobenzene under heating at 130 degrees. Then I added the dropwise naphthopyran with silane. When I obtained a gel, I put the gel in a Teflon mold, and the Teflon mold was inserted in vacuum oven for 2 days under heating at 70 degrees. Here I report the picture of my film, and I calculated a gel fraction of 64%. Then I have performed preliminary studies on PEMA film to test the mechanochromic behavior of the molecule. In particular, I scratched the molecule, and as you can see under fluorescent lamp, it seems that there is a change of color. Then I heated the film, and there was the disappearance not only of the color, but also of the stretch. To conclude, naphthopyran was successfully synthesized and characterized by NMR spectroscopy. The mechanochromic behavior of naphthopyran was tested, and I have to perform a mechanical analysis on the PEMA film. I want to thank VIT and Intercos Group for giving me the opportunity to attend the PhD program. I want to thank the organization committee too, my research group, and I want to thank you for your kind attention.
Thank you, Rosita. Are there any questions? Okay. If not, will you use these materials for which application?
For example, automotive industry, for structural materials.
Okay, thank you very much. We can thank again Rosita. So the next speaker is Gioacchino Pignatiello, with his work about enhancing tire performance through effective dispersion of bio-based components in rubber compounds. Okay.
Hello everybody, I'm Gioacchino Pignatiello from University of Napoli Federico II, and today I talk about enhancing tire performance through effective dispersion of bio-based components in rubber compounds. Tires are complex systems made of more than 10 ingredients, subdivided in 4 macro categories. Okay, so tire are complex system made of more of 10 components, subdivided in 4 macro categories, such as rubber, like natural rubber, polybutadiene, and the SBR. Of filler, of which the most important are carbon black and silica, curing agents that contains vulcanizing package that is used to make network between elastomeric chains, and other additives like plasticizers, antioxidant, organic acid, and so on. Plasticizers recover an important role and are not negligible in elastomeric compounds because they are present up to 20–30%. So why not replace fossil plasticizers with bio-based one? Effectively, this is the aim of my PhD project, the substitution of more or one fossil bio-based plasticizers with bio-based ones. But this is not a simple passage, but is a very critical passage for many aspects. It's possible to have incompatibility of components, the dispersion of filler in rubber may be affected, and the recipe of compound and the process will be changed. But it's not only important to increase sustainability. The most important thing is increasing sustainability, but without affect the performance. So the crucial way is to balance performance and sustainability. So in this first period, I prepared 18 compounds with different formulation produced by batch mixing, varying SBR-BR matrix ratio, using 40 pHr of silica, plasticizers, bio or fossil, and other additives. I used the Amber-Bender mixing process, divided in 3 phases. After every phase, I obtained a master batch. The third master batch is the unvulcanized rubber. This is put in compression molding press in controlled temperature and pressure to obtain vulcanized rubber. The first characterization that I made in this period are regarding mechanical properties using a tensile test machine. This is reported a characteristic vulcanized rubber stress strain curve, and the most important parameters are tensile strength and elongation at break. By comparison of compound based on bio and fossil formulation, is evidence that the compounds that contains bioplasticizers show a higher tensile strength than those containing fossil plasticizers. The same things, and so best results are for the elongation at break. But this is a surprising result because one may expect that fossil plasticizers are more compatible with the elastomer matrix than bioplasticizers. But is not only the parameters to take in account. So, but is also important to relate process and mechanical properties. In effect, the curve torque with, versus time in the case of a fossil plasticizer show a decrease of torque for 1 minute. That is not good dispersion because the mixing in this time is lower than the case of bioplasticizers. So this is for because the fossil plasticizer make for the compound a slipping. So this cause also a temperature reach for the plasticizers bio-based compound reach the softening point in a larger time. So it's really important to characterize the compound in terms of morphological analysis like TEM, to study and investigate the filler dispersion, and in terms of the electric spectroscopy analysis, to correlate between the electrical properties and the mesostructure to optimize the compound formulation. Are also important structural and functional analysis, such tensile test and DMA, to have an evaluation of the final performance of the compound, such as wear resistant and wet grip. It's also really important to relate experiments and theory, studying the Hansen solubility parameters theory that take in account polar H-bond and the disperse interaction between two or more ingredients of the compound to predict the filler dispersibility that plays an important role in the performance of tire, and this in particular in the case of a bio-based formulation to increase the sustainability. Thank you for your attention.
Thank you, Gioacchino. Are there any questions? Okay.
Thank you for the nice presentation. Just a quick question. Do you perform any kind of migration assay for your type of plasticizer?
I use the resin plasticizers. Resin plasticizers are really important to control the process parameters and also to modulate final properties of the tire. And so I compared the bio and fossil plasticizers, particular resin.
Thank you.
Are there any questions? If not, we can go ahead and thank again Gioacchino.
Thank you.
Okay, so the next speaker is Nicola Porcelli, showing his work about synthesis of bio-based monomers and polymers.
Hello there. I'm a first-year PhD student from the University of Modena and Reggio Emilia, and I'm here today to share with you the details of my PhD project, which is about the synthesis of bio-based monomers and polymers, as the title says, which is purposely generic since the subject is broad, as I will show you. First, I would like to show you the context in which this project was started. The enterprise which is financing the project, later called SPA, is working in the construction field, producing binders and mortars for the constructions. Well, in 2018, the European Union banned the use of bisphenol A across all country members due to his high toxicity as an endocrine disruptor, which left a huge vacuum to fill in the polymer industry, since it was largely employed in the production of polycarbonates and most famously for the production of DGEBA, which is one of the main components of an epoxy resins. Well, this left a huge vacuum to fill, and this prompted the research world in finding greener, more sustainable and less toxic alternatives to such compound, and this is the framework in which I'm working. For agreement reasons, I cannot share with you all the details of my work, And I've picked up some examples I think are interesting. So, the main goal of my PhD is finding sustainable alternatives for the production of olefins deriving from agricultural waste, since those waste streams are of particular interest for the research world due to their high availability and low cost. And the focus on olefins in particular is due to the fact that those compounds can be either used in the production of traditional olefin by traditional radical polymerization, or in the production of epoxy compounds by a variety of means. For this reason, I targeted some compounds that are now quite expensive to produce. Among those, some vinyl derivatives of sugar derivatives and lignin, the polymerization deriving monomers. Among those, guaiacol and syringol. And of course, methacrylates, as my research group in Modena is also working on atom transfer radical polymerization, which is a controlled radical polymerization technique. And also, the other part of my work is the synthesis of aromatic cores to use as cores for epoxies. So, up to now, I've been working on the production of amine hardening agents for epoxy resins, starting from lignin-deriving phenols. Those are the compounds I'm most proud of, since those gave the best results, and I think these are quite good examples of the differences in reactivity between the various substrates deriving from lignin. Those compounds underwent chloromethylation through a blank Calais reaction involving hydrochloric acid and paraformaldehyde to afford the chloromethyl derivative, which went under nucleophilic substitution with formamide and then hydrolysis to afford the corresponding diamine. Later then, I focused on derivatization of sugar derivatives, namely furfural and furfuryl alcohol, and lately I've been focusing on the production of furyl acrylic acid and the study of its reactivity. I found it particularly interesting since this compound can undergo photocyclic addition, as it is reported for its analog, the cinnamic acid, and I'm interested in producing its cyclobutane derivative, but it also undergoes oxidative ring opening through such reaction, producing the unsaturated decarboxylic acid, which I'm currently studying. Problem is with this compound that the synthetic route is kind of a nightmare due to the fact that it leads to a mixture of stereoisomers. So its reactivity is a bit unpredictable and it requires long reaction times to produce. The goal there is producing terephthalate-like structures to use for coatings, like glyptal, which is a derivative of orthophthalic acid. One last thing that is a side project deriving from the last conference I've been at, and I wanted to study the reactivity of vanillin, which is also deriving from the oxidative depolymerization of lignin, and for doing so, I functionalized it with methacrylate, producing the corresponding methacrylate, which I plan to polymerize by atom transfer radical polymerization to afford a well-tailored polymer, and then cross-link it by imine bond formation, which will allow me to produce vitrimeric materials. This last step proved to be the most difficult for now, since imine bond formation is a type of chemistry that is a bit counterintuitive, since it requires acidic catalysis and water to be performed, but on the other hand, those same conditions revert the process. So if there's anyone who has been working on that, and wants to shed some light on it, it would be really well appreciated. So, to sum up, until now I've been able to achieve a reasonably sustainable procedure for the production of lignin-deriving amines. One for the ring opening of a furfural derivative with reasonable yields, and the production of this vanillin methacrylate. What's left to do is the field testing of those bio-based amines as hardening agents in epoxy resins. The start of the study of the post-cyclodation of furfural derivatives, since our XRD, which is necessary for determining the structure, is currently out of order, and then the cross-linking of polyvanillin methacrylate. I would like to conclude thanking my fellow colleagues, which are also present here, and you for having me there. This is my contact in case any one of you is interested in my work.
Thank you, Nicola. Are there any questions? Okay, just one. If you did perform any scale-up of your synthesis?
For now, I did it just for the amine production, and I'm quite proud of the fact that we went from milligram scale to 10 to 20 gram scale for now, and we were able also to reduce the amount of acid and solvents involved to half of the initial amount. So imagine that for 1 gram we started working with 20 milliliters of hydrochloric acid, and we were able to scale it down to 8. So yeah, it's not a full scale scale up, but it's a starting point.
Yes, of course. Thank you. So we can thank again Nicola. Okay, the last speaker of the session is Susanna Romano, showing her work about starch films plasticized by novel dicationic imidazolium-based ionic liquids. Ma la presento?
Hello.
Okay, you can start.
So, thank you, Benedetta, for the introduction. And as she said, our work was focused on the production of starch film plasticized by dicationic ionic liquids, based on imidazolium-based ionic liquids. So, just quickly to find a place for our work into the different fields of research. As everybody knows, the biggest current problem is the huge use of common plastic materials, and so consequently their waste and the related pollution. So the challenge of these years is to find new materials which can be, first of all, degraded to the environment without risk, and also that can be easily processed as the common plastics. That is a key aspect of the production, and of course that are can be low-cost materials. Among them, a suitable alternative of these alternatives can be biopolymers, and among them starch is one of the most promising, because starch is a low-cost material, and first of all. It's easy to find in nature because it's one of the most abundant polysaccharide, and of course it's non-toxic. But linked to its structure, starch has some drawbacks, which imply low mechanical properties, high solubility, and brittleness. So to overcome these limitations, the introduction of some compounds called plasticizer is needed to weaken the interaction between the polymer chains and to improve the processability. Ionic liquids are widely used for this purpose, also thanks to their unique properties. They are organic salts with a melting temperature below 100 degrees, composed of anions and cations. As I said, they have some unique properties, such as the low volatility, the good conductivity, the high thermal and chemical stability, and the aspect that is underlined in this work is the possibility to design these compounds for our purposes. In fact, there is a new, very attractive category of ionic liquids that are the decationic ionic liquids, in which there is a very large number of possibility to combine cations and anions, and also the introduction of a linker in the new variation of the cationic partner between the two, in this case, imidazole rings. This tunability allows us to produce material that are very versatile and useful for different applications, such as packaging, tissue engineering, and flexible electronics. The films are prepared by the classic solution casting technique, and they were then characterized by different methods. And talking about the ionic liquids, they were synthesized in a one-step reaction, changing the linker between the two imidazole rings. And in this work, the influence on the linkers on the film properties will be evaluated. So starting from the analysis of IR spectra, it was possible to study the different interaction of each plasticizer with the starch structure, and in particular by observing the absorption band linked to the hydroxyl group stretching, we can see that there is a shift to higher wave number. That means that there is a good weaken action between the polymer matrix and the plasticizers. In addition, through the thermogravimetric analysis, it was possible to study also the increasement of the temperature of degradation of these materials, showing again that the linker length influenced the degradation of the materials, and this is a good aspect of for the processability. The water contact angle measurement provides useful information about the hydrophobicity of these materials, because we know that a material can be considered hydrophobic if the angle between the water drop and the surface is more than 90 degrees. And as you can see, the values for the films are quite high, really close to the hydrophobicity threshold. But we can notice one thing, that is the more the linker chain is, the more the separation between the polymer chain is promoted, and so the wettability is higher by the linker length increasement. And the same trend is followed also by the values of water uptake. So an interesting aspect is the conductivity of such materials, and we were able to study that aspect through the electrochemical impedance spectroscopy, just putting the film between two steel stubs and measuring the resistance of the materials. And again, you can see that the type of the linker really affect the values of conductivity and electrical properties of such materials. And again, when the separation from the polymer chain is promoted, there is an easier ion migration in the matrix. We also evaluated the mechanical properties of the starch films, and we can see that when the two imidazole rings are very close to each other, the values are very high compared to the other films, in which the Young modulus and the tensile strength decrease and the elongation at break increases, confirming that there is a higher mobility of the chain in the matrix. Last but not least, a very interesting aspect of this use of ionic liquids in this kind of materials is that the decationic ionic liquids has a very interesting antimicrobial activity, and even more interesting in comparison to the monocationic one. So we evaluated the minimum inhibitory concentration of these salts by the broad microdilution method against two bacteria strains, 1 gram-positive, that is Staphylococcus epidermidis, and the gram-negative Pseudomonas aeruginosa. The salts showed interesting antibacterial activity, especially against the gram-negative, the PAO1, and in particular, the lower MIC values were reached by both the C5 and the benzylic linker, confirming again that you can just play with the combination of linkers to obtain useful properties and very several kind of properties of such films. So to sum up, we prepared starch film, versatile starch films with 3 different dicationic ionic liquids. And in the synthesis, we changed the linker between the 2 imidazole rings. We found out a correlation between the film properties and also the salt properties with the type of the linker used in the synthesis. And also we found that these materials have good conductive property and an antimicrobial activity. These tests were about the antimicrobial activity were performed in solution. So one of the future perspectives will be to evaluate this activity also of the films, and also to continue the study on further different linkers. Moreover, we want to also expand the research on the potential antioxidant activity of these salts, and in a more ecological perspective, we intend to replace these salts with those of natural origin. So thank you for your attention. And I want to thank also my colleague Benedetta, who worked with me in this project, and also to celebrate her birthday. Thank you.
Thank you, Susanna. Are there any questions? Okay, if not, just a quick one. What about the cytotoxicity of your dication?
Okay, we are testing the cytotoxicity, but in literature is just known that the dicationic are less toxic than the monocationic ones, so it's a good start from the test, and we are starting to perform it. Thank you.
So we can thank again Susanna. So the session is ended. Now it's the coffee break, I think.
No, non sapevo più che blocco post pranzo.
Welcome back from the coffee break, and this is the last session of today, so we will be quick. The first speaker is Francesco Scorcioni, and he will talk about chemical recycle of plasmics.
Okay, thank you. Good afternoon, everyone. My name is Francesco, and I'm a PhD student in industrial chemistry from the University of Bologna. I work in the research group of polymers with professors Benelli and Giorgini, and my research project is in collaboration with the company Versalis. My research deals with the study of chemical recycling of mixed plastic waste, also called plasmics, by pyrolysis reaction. Okay, plasmics by definition is the set of heterogeneous plastics included in post-consumer products and that cannot be recovered as individual polymers. It is an important fraction of the total plastic waste, about 50%, and while for the plastic waste collected via separate waste collection can be easily treated by different recycled technologies, such as, for example, mechanical recycling. That's not the case for plasmics. That to date is treated by mainly treated by incineration and landfilling. That are two techniques with strong environmental impact. So it's necessary to develop new chemical recycle technique that can capable of treating this type of complex and variable materials. Pyrolysis, as you know, is a very flexible and versatile technique that involves a heat treatment of materials in an inert atmosphere to convert it into simpler molecules that can be conveniently used as chemical intermediates or products. There are mainly three types of products that derive from the pyrolysis process. So an incondensable fraction consisting of CO, CO2, hydrogen, and like hydrocarbons, characterized by a high heating value. This product can be used, for example, as a fuel to contribute to the energy demand of the pyrolysis process itself. A condensable fraction, also called the pyrolysis oil, consisting of a complex mixture of hydrocarbons whose nature depends on the feedstock. And this is often, such as in my project, their most valuable product thanks to its industrial potential. And finally, a solid carbonaceous residue that contains all the inorganic compounds that plastic products are additivated with. With this in mind, the aim of my project is to develop a chemical recycling technique that can complement mechanical recycling and other mechanical recycling techniques currently used to improve globally the circularity of plastic products. And more in detail, the goal is to convert mixed plastic waste into, by pyrolysis process, into a pyrolysis oil that can be easily inserted in a petrochemical industry value chain for the synthesis of new polymers from recycled feedstock. Our work mainly involves two steps. First, we study the chemistry of the pyrolysis process. So we carry on pyrolysis tests both on individual polymers and their combination in order to understand the synergistic effects that exist between the different components of plasmics. And after that, we study and optimize the condition parameters in order to maximize the target product, that is a pyrolysis oil with a good quality. Now I show you some examples just to give you a better idea of how we work. So we start by studying individual polymers, and then we combine it for study the synergistic effects. So for example, here I report the mass balances obtained working on polyolefins. So for example, low density polyethylene, polypropylene, and their mixture, or polystyrene matrix. And of course, different type of polymers give different product and different fraction, different mass balances. Here I report the results obtained from a compositional analysis of oils obtained from these polymers that are arranged for simplicity into fraction according to the hydrocarbon chain length of product and into Piona classification according to their chemical nature. Piona stands for paraffin, isoparaffins, olefins, naphthenides, and aromatics. And we see that based on the type of feedstock, we obtain different kind of products with different industrial applications. So for example, from the pyrolysis of polyolefins, we obtain an oil consisting mainly of olefins and paraffins in the C5, C15 range, while in the pyrolysis of polystyrene, we obtain, of course, aromatic products, such as, for example, toluene, xylene, and styrene. The pyrolysis of chlorinated polymers, such as PVC, needs particular attention because the pyrolysis of these polymers generated acidic and chlorurated organic products that can, from an operative point of view, generate problems during the process. So we study the effect of an alkaline reactant for the abatement of this type of product in the condensable and incondensable fraction, and we see that additivating the alkaline reactant with the polymers treated, we obtain that the chlorine content shifts from the condensable and incondensable fraction to the solid residue. So the quality of the condensable and incondensable products increase. To conclude and to summarize the presentation, future developments of this work are understand all the synergistic effect that exists between the component of plasmics, carry on different tests on different polymers and other components that constitute plasmics in order to realize a flexible and a flexible recycling technique capable of treating this type of complex and variable matrices and maximize the target product that is a pyrolysis oil, a naphtha-like pyrolysis oil for its insertion in the petrochemical industry value chain. So I finished the presentation and I want to thank you all for the attention.
Thank you for the presentation. Are there any questions? Don't be shy.
Thanks, Francesco, for your presentation. My question is, if possible, to increase the selectivity during your pyrolysis project with the use of catalysts, for example, in order to have a selective pyrolysis to control the production of a specific side product during the process?
Okay, thanks for the question. We just started to studying the effect of catalyst. That, of course, it can be a good way to optimize the process and to obtain a specific kind of product. So for our application, the catalytic aspect is very important and very fundamental. So yeah.
Are there other questions? If not, yes, okay, sorry.
Hi, thank you for your nice presentation. I was wondering about the green aspects of the pyrolysis. Do you have any byproducts, any waste, or it's quite clean?
Yeah, the most important byproduct is the solid residue. So, as I told, it contains all the inorganic impurities, all the inorganic additives, that plastic products are additivated with. So the objective is often to minimize this product and increase the condensable and incondensable fraction that have different industrial application. For industrial application of solid residue, it needs a different kind of treatment, and it's very difficult to purify it and use it in different applications. So
let's thank again Francesco. And welcome our next speaker, Giulia Scurani, who's talking about bifunctional ATRP initiators for the synthesis of dichloropolystyrene. When you're ready.
Good afternoon. Today I'm going to talk about the synthesis of bifunctional initiator for the atom transfer radical polymerization and their influence on the thermal stability of the final polymer. Atom transfer radical polymerization consists in a dynamic equilibrium between active and dormant species mediated by a transition metal catalyst usually associated with nitrogen ligands. The concentration of the radical is kept low and constant during all the reaction. In this way, we can obtain polymer with predefined molecular weight and also control over composition, topology, and functionality and low dispersity. The functionalities can be introduced into the polymer backbone in different ways. The one that I want to explore today is the introduction of functionality by the use of functional initiators. In 2015, Altintas and his co-workers already explored the possibility to introduce functionalities by using a bifunctional aliphatic halide ester initiator into polystyrene. They highlight reduced thermal stability of the resulting polymer when treated at 200 degrees centigrade for 24 hours, with a reduction of the chain length and also a loss of mechanical properties of the final polymer. From an industrial point of view, it's important to satisfy specific requirements, such as the mechanical properties. So it's important to know and also understand the thermal and thermomechanical stability of the final polymer. So when we introduce an initiator into a polymer containing some functionalities, we have to be sure that they lead to thermostable polymers too. The solution found by Altintas is to introduce a triazole functionality inside the mid-chain of the polymer backbone. What we think is to improve the thermal stability of the initiator by implementing different different portion of the molecule. So we introduce an aromatic core that is more thermostable than the aliphatic one, and also an amide group that is more thermostable than the ester moieties. So we start from the synthesis of this initiator that consists in two steps. The first is the production of the acyl chloride, and the second is a nucleophilic substitution by a diamine. We obtain the molecule in high yield and also good purity, as you can see from the NMR spectra. Then we employed it into the Arjet ATRP of styrene using copper chloride TPMA as catalyst ascorbic acid acetonide as a reducing agent, and trimethylpyridine as organic base. We obtain a polymer. This is the proton NMR spectra that show us the livingness of the polymer, highlighted by the hydrogen adjacent to the chlorine terminal group, and also the broadness of the peaks of the initiator, confirming the inclusion of the initiator inside the polymer backbone. Then we tested the thermal stability of the resulting polymer, and we observed that we observe an increase in the thermal stability of the final polymer. We had a reduction of the chain length of only 16% when treated at 230 degrees centigrade for 1 hour. So we are satisfied with this result, but we want to explain the reason why the initiator used by Altintas is unstable. So we move to the ester moieties, the aromatic ester initiator. We synthesize it in the same way by replacing the diamide with adiol. We obtain it in high yield and also good purity, and we employed it into the atom transfer radical polymerization. The same consideration of the proton NMR spectra can be done for this initiator. Then we tested again the thermal stability of the resulting polymer. We observe that also this polymer is thermostable. So we move to the aliphatic initiator, the corresponding aliphatic initiator, both the ester and the amide. We synthesized the initiator. We had a problem with the starting material, so we replaced it with already available bromide, acyl bromide, and we synthesized the true initiator containing the bromide group. These are the two polymers that are obtained with this initiator, with the peaks of the initiator and also the livingness of the polymer. However, when we analyze them by GPC, we observe a bimodal behavior of the molecular weight. We are going to hypothesize we do some hypotheses on this bimodal behavior because we want to avoid this. And we hypothesized the presence of that can we can have this bimodal behavior for a mixed halogen exchange system inside the reaction, and also a presence of both mono and bifunctional initiator inside the reaction mixture. But we are going to investigate it more. So finally, we synthesized this for initiator, and we tested the polymer for the aromatic initiator, the thermal stability for the aromatic for the polymer obtained by the aromatic initiator that are quite good. In future, we want to tune the ATRP for the aliphatic initiator, and also replacing the bromide group with the chlorine one. And we want to avoid the bimodal behavior, so we want to tune better the polymerization, and then tested the thermal stability of this polymer. And finally, we want to hypothesize a possible mechanism for the reduction of the chain length. Finally, I want to thank all my research group and Carlo Buonerba Research Center in Versailles that analyzed my polymer, and also you for your attention.
Thank you, Giulia. Are there questions for her? No? Everyone is too shy? Okay, I have just a curiosity. Is your synthesis a bulk synthesis, or do you need solvent? Because
No, we need solvent. We do the synthesis in dichloromethane.
Ah, okay.
No, the first step is in bulk. So we put the reagent and the thionyl chloride in at 60 degrees centigrade, so it reflux, and then we obtain the product in bulk. The second step, we use the chloromethane.
Yeah. Okay, thank you. If there are no more questions, okay, let's thank again Julia. Now we have 2 students. We are done with the PhDs for today. And let's welcome Alice Biannucci. And she's talking about exploring the effect of the applied thermal treatment on the fractal behavior of NBr silica compounds.
Good afternoon. Today I will talk about part of my thesis project, and in particular I will focus on the effect of the applied treatment on an elastomeric NBr compound filled with silica. Nitrile butadiene rubber is an unsaturated synthetic copolymer and of acrylonitrile and butadiene. In particular, the polarity of the acrylonitrile monomer confers the compound a good resistance to oils and fuels. Therefore, it can be used for hoses, cables, and seals in contact with these chemicals. Moreover, this compound is used also to make shoe soles. More specifically, the material used in my project is an NBr compound filled with silica and cross-linked with sulfur. The cross-linking was achieved by keeping the material for 5 minutes at 170 degrees, and the company that provided the material provided also a torque time curve obtained at the cross-linking temperature, from which no signs of degradation of the material are visible if the material is kept at a high temperature for about 30 minutes. In order to study the effect of the applied thermal treatment on the fracture behavior of the material, 3 thermal histories were considered. The first one corresponds to the virgin material, therefore it was kept at 170 degrees for 5 minutes, which corresponds to the cross-linking thermal process. The second one consisted in further 5 minutes at 170 degrees, therefore the total time at high temperature was 10 minutes. While the third one consisted in additional 28 minutes to the cross-linking process, therefore the total time is 33 minutes. A preliminary characterization of the material was performed in uniaxial tension, performing tests on dumbbell specimens. And it can be observed that the two thermal treatments have a similar effect on the virgin material. And these results were supported by the ones obtained by the estimation of the cross-linking density, which was performed through swelling measurements in Tolwyn. And these measurements showed similar cross-link density for these 2 materials. Comparing if the curve of the virgin material, which is highlighted in red, is considered, we can observe that the 2 thermal treatments have a stiffening effect, and this suggests that the cross-linking process was most probably not completed after the curing process. Next, the focus was shifted to the fracture behavior of the material. Indeed, a proper characterization of the fracture properties of elastomeric compounds is needed for a correct design of the objects used in practical applications. And in particular, the use of the ultimate properties in uniaxial tension, therefore the stress and strain at break, is not fully representative of the behavior of the material, since in this case the samples break in correspondence of flaws and defects of the material on which we don't have any control. The fracture behavior of the material was studied using pure shear specimens. A notch was created at half height of one edge of the specimen, and in this way the crack will start from a defect which has controlled dimensions. The samples were loaded in mode 1 at room temperature and in displacement control at 20 millimeters per minute. And the tests were also video recorded. What is obtained is a force displacement curve, and the fracture toughness can be evaluated using the J-integral approach. And this quantity depends on the geometry of the specimen, on the length of the notch, and on the input strain energy up to the crack onset. The parameter eta is a dimensionless shape factor, which is equal to 1 in the case of the used specimens. In order to better understand the effect of the thermal treatment on the structure of the material, the focus was put not only on the crack onset, but also on the stable propagation of the crack. In this phase, the crack propagates only as long as the load applied to the samples is increased, while it stops propagating if the load is stopped. The end point of this phase is represented by the point at which the maximum force is reached. And after this point, we have an unstable propagation of the crack, which is characterized by higher velocity, and moreover, the crack will spontaneously continue propagating even if the loading is stopped. The plot on the right represents the force displacement curve for the 3 thermal histories considered. And in particular, the red lines represent the virgin NBR, while the purple and green lines represent the thermally treated materials, with the green lines representing the longest thermal treatment. The full dots represent the crack onset, while the star-shaped symbols represent the maximum force. What can be observed is that both the maximum force and the displacement at which the maximum force is reached are decreased in presence of more severe thermal histories. The J-integral was evaluated not only at the crack onset, but also at the maximum force. And if the crack onset is considered, it can be observed that the effect of the thermal history is very small, while if we consider the maximum force, we can observe that the fracture toughness of the material is strongly reduced in presence of more severe thermal treatments. If a comparison is made with the ultimate stress and strain in uniaxial tension, it can be observed that the thermal history has a slight effect on both the stress and strain at break. Therefore, to conclude, we can say that if the material is subjected to different thermal histories, the stress and strain at break in uniaxial tension are only slightly affected. And the same conclusion can be derived considering the J-integral at the crack onset, while if the maximum force is considered, we have a significant effect of the thermal treatment. These results highlight the importance of considering not only the crack onset, but also the propagation phase while studying the fracture properties of the material, of elastomeric materials. And thanks for the attention.
Thank you, Alice, for the nice presentation. Does someone have a question? Yes, we have one.
Thanks for the presentation. Just a curiosity. Are you going to study also different kinds of silica or silica compared with carbon black to understand the effect of the dispersion of the filler on the mechanical properties?
So the silica that I used is pre-silanized silica, and the material was provided by the company, but we have, like, my thesis work is part of a broader PhD work, and they are studying other type of materials with other type of silicas and fillers.
Clear, thank you.
Are there other questions? Well, if not, let's thank again Alice. And now the last speaker for today and the last student, Luca Spagnoletti, who is talking about viral assisted delivery of polythiophene-based nanoparticles to rescue neurodegeneration.
Okay, thanks for the kind introduction and good afternoon. I'm a master student from the University of Genoa doing his thesis at the Center for Synaptic Neuroscience of the Italian Institute of Technology. My work aims at developing a new strategy for treating neurodegenerative diseases which makes use of polymeric semiconductive nanoparticles. Neurodegeneration is a major threat for an aging population, consisting in the progressive death of the neurons composing our nervous system. This leads to a gradual impairing in the cognitive and motor functions, with manifestations like memory loss, tremor, or unbalanced movements. Despite many therapies are available, none of them plenty fulfill the desirable safety or effectiveness criteria. For instance, levodopamine administration, a precursor of dopamine used for treating Parkinson's disease, suffers from a progressive lack of efficacy. On the other side, deep electrical brain stimulation requires the implantation of an electrode inside the brain, so it is invasive. Lastly, optogenetics require the genetic modification of the organism, so it is unfeasible in humans. A new promising solution comes from the use of poly-3-exylthiophene. This semiconductive polymer is extensively used for making organic photovoltaic cells due to its property of turning visible light into excited electrons. In analogy, it has been proposed that negative charges created upon light irradiation of nanoparticles made by this polymer may be able to depolarize and so stimulate a denervated neuron. Now this has already been tested in animals blind due to retina neurodegeneration, producing a significant improvement in their vision. What I aim to do is the delivery of those nanoparticles for treating diseases that are located in the brain. This has two main issues. The first one is how to reach the brain. In fact, there is a barrier that is called the blood-brain barrier that physically separates the blood from the brain and is impermeable to most drugs. The second is how to target only the neurons affected by the disease. The way we decided to exploit is the functionalization of the nanoparticles with a bacteriophage virus that you can see in the figure. Now this virus is completely safe for humans as it is not infective for our cells and is only used as a nanoparticle vehicle. But why this virus? First of all, it can be easily engineered for expressing an element that can target specific neuronal subpopulation. Moreover, this virus has the potential for crossing the blood-brain barrier, so it possesses both the characteristics that we need for our nanoparticles delivery. Now, considering that the virus exposes thousands of protein primary amines, we developed a polymer possessing one NHS-activated ester for every 2 thiophene ring. The NHS, or N-hydroxysuccinamide, makes the polymer very reactive towards nucleophile, in our case, the phage amines. Our final goal is to bind the multiple nanoparticles per phage unit, using the latter as a nanoparticles carrier. Now, the nanoparticles has been synthesized by a method called reprecipitation that is based on the fast precipitation of nanoparticles that takes place when a solution of a polymer is dropped in a solvent in which the polymer is not soluble, water in our case. We optimized the polymer concentration and the volume of solution dropped in water in order to maximize the nanoparticles number without having aggregation of the nanoparticles that is deleterious for the reaction with the phage and then their transport in the brain. Here you can see the characterization of the nanoparticles, which appears to be less than 40 nanometers in hydrodynamic diameter and of reproducible synthesis. As expected for nanoparticles used in photovoltaics, we observed an absorption of visible light. Lastly, we tested their colloidal stability using agarose gel electrophoresis, with a narrow band of nanoparticles confirming it. Before moving to the functionalization with the phage, we wondered if those nanoparticles were effectively able to covalently react with proteins. For this purpose, we made react with the same amount of IgG, that is an antibody used as protein representative, two nanoparticle samples. The one on the left, in which all the NHS group have been hydrolyzed before the reaction with the IgG, so those nanoparticles are no longer able to covalently bind the IgG and are used as a control for non-covalent interactions. The one on the right, that are freshly synthesized, and so they should retain all the NHS group and in theory be able to covalently bind the antibody. It is known that an incubation in sodium dodecyl sulfate, that is a surfactant, is able to linearize and so detach any non-covalently bonded proteins without affecting the covalently bonded ones, as this procedure is not able to break covalent bonds. After that, we ran both of them in an electrophoretic gel. As expected, we observed an almost total recovery of the antibody from the non-covalent interacting sample. However, no free IgG was detected from the supposed covalent one, proof of a high yield of the reaction between IgG and nanoparticles. Therefore, we moved to the functionalization with the phage. Here, while the hydrolyzed nanoparticles used as a control only shows two independent bands on the gel, one for the nanoparticles and the other for the virus, the non-hydrolyzed NHS nanoparticles shows a third band that is compatible with a product of functionalization that is bigger and so cannot permeate the gel. To confirm our hypothesis, we resuspended the content of the well and we acquired its UV visible spectrum, which correspond to the overlap of the nanoparticles and the phage individual spectra, proving that this product is composed by both of them. Finally, we acquired a 10 micrograph of the sample, which clearly shows a successful conjugation between nanoparticles and phage. So, in summary, we have been able to functionalize the nanoparticles first with an IgG, proving their reactivity towards protein, and then with a bacteriophage virus, leading for further biological applications in rescue neurodegeneration by photostimulation, especially if a more red-shifted version of the polymer will be made available, allowing a skull external far red stimulation of the impaired neurons. Thank you very much.
Thank you, Luca, for the nice presentations. Are there questions for him? Yes.
Prova? Okay. Thank you for your presentation. I have a question about the polymerization. You said that the polymerization is carried out by pouring the monomer in water. Okay.
No, so actually, this is the polymer, and we don't synthesize it. This is made by a group at the CNR of Bologna, the Professor Di Maria. We take this polymer and we synthesize the nanoparticles made by this polymer with this method. So here there is the polymer dissolved in an appropriate solvent. And so this method is only used for making from this polymer the nanoparticles of the polymer. Thank you.
Okay, thank you.
Hi, thank you for the nice presentation. I have just one curiosity due to my complete lack of knowledge in this topic. Do you have any idea of the removal of the particles after the application on the brain, like how they are removed and safely, if there is any side effects of this system?
Thank you for the question. This is a very nice question. So, first of all, we hope that the nanoparticles are not removed because for being active, they have to stay there. We don't have any data in the brain because we didn't perform the experiment. However, we have some data from these studies that are subretinal injection of nanoparticles, and they stay for months. So, yeah, in I mean, if this result is representative of the brain, maybe 2 or 3 months is the time that nanoparticles can stay. And they observed a total lack of toxicity of this polymer.
Hi, sorry, I catch the opportunity. Related to this, in these studies, there are some information about the dimension of the nanoparticles. Do you reach the dimension that you have to?
Thanks for the question again. So yes, in these studies, the nanoparticles are bigger than mine. The way we decided to try to synthesize smaller nanoparticles is because, first of all, they have a higher surface, so they are more likely to react with the phage. Then, second, these phage carried with nanoparticles have to pass through the blood-brain barrier. Now, we know that this transport should be an active transport, so it's not due to diffusion, so it's likely that maybe a bigger dimension would not be a problem, but I mean, we are not sure, so the best way is to keep this as small as possible.
Thank you very much for the nice talk. Just a curiosity, I suppose colloidal stabilization in this case is provided by, electrostatic interaction, right? Through hydrolyzed activated esters, correct? Yeah. Do you foresee any need regarding having a sort of stealth shell on these particles, considering that you are foreseen to apply them anyways in blood or across the blood-brain barrier?
Sorry, can you elaborate?
No, I mean, are you concerned about any interaction between these particles that are basically naked and serum proteins?
Okay, no, not yet, and it's something that we will probably have to perform. However, keep in mind that we are not interested in the stability of those nanoparticles in the blood, but of this construct of nanoparticles plus phage. And yes, for sure, we will have to test their stability in the blood. We have preliminary data of the stability of a construct made by virus and fluorophore attached in the same way. So let's say instead of the nanoparticles, we have a fluorophore, and they appear to be stable in human plasma and in animals in which it has been injected. But we don't have any proof of stability of this construct. Thank you.
Thanks a lot.
If there are no more questions, no? Okay. Let's thank again Luca. And this session is finished, and we will see each other for dinner at 8:30.